Good morning. I'd like to welcome everyone back to the Part 450 workshop, day 2. Today, we had a great day yesterday, and we covered a lot of ground. We went through subparts A and B. We did an overview with a discussion about pre-application consultation, and we just started into subpart C, our safety requirements. Today, we're going to continue that discussion. We have up first, we have one of our last hazard control strategy, and then we're going to start going into the rest of subpart C. So today, to kick it off, I wanted to give some more reminders to folks. Our charts are available on our website, and that is faa.gov/space. And then on the left nav bar, it says Streamlining Licensing Process, and that is our Part 450 website. It has all the charts for today. It has a copy of the regulation, all of our ACs, means of compliance table, and all the things that you'll need to be smart on Part 450. Also, as a reminder, please keep the questions and answers coming throughout the sessions using the Q&A function on the webinar. That way our team will have those at the ready, and then for our Q&A sessions, we can go through those more quickly. Also, if you have any feedback for us, please go ahead and just throw that into the chat. We're going to be doing these workshops more frequently, once a quarter. And if you have some feedback for us on that, that would be wonderful. Okay, without any further ado, we're going to be talking on Flight Abort 450.108, and I'd like to introduce Mr. Tom Ricketson.
Thank you, Michelle, and good morning, everyone. It's my pleasure to walk you through the Part 450 requirements on Flight Abort, which cover when a flight safety system must be activated. Section A deals with applicability and states that 450.108 applies to use of Flight Abort as a hazard control strategy for the flight or phase of flight of a launch or re-entry vehicle to meet the public safety criteria of 450.101. Next slide, please. Section B describes requirements for flight safety systems and was mentioned in yesterday's workshop. Section B1 says that an operator must use a flight safety system that meets the requirements of Section 450.145 if the consequence of any reasonably foreseeable failure mode in any significant period of flight is greater than 1 × 10⁻² conditional expected casualties in uncontrolled areas. Section 145 contains requirements for the highly reliable flight safety system. And we'd like to note that an example means of compliance for Section B1 of 108 is Range Commanders Council Standard RCC 31919, Flight Termination Systems Commonality Standard. Section B2 says that an operator must use a flight safety system that meets the requirements of Section 450.143 if the consequence of any reasonably foreseeable failure mode in any significant period of flight is between 1 × 10⁻² and 1 × 10⁻³ conditional expected casualties for uncontrolled areas. So that's a smaller number of conditional expected casualties. It does not require the highly reliable flight safety system. It refers the applicant to Section 450.143, which is on safety critical system design, test, and documentation. Next chart, please. Okay, limits of a useful mission. We're going to talk about regulations related to the limits of a useful mission in a section later on trajectory analysis, but we need to introduce the topic now to facilitate the flight abort training. So I'm going to start with the definitions that are in the bottom box. This state limits of a useful mission means the trajectory data or other parameters that bound the performance of a useful mission, including flight azimuth limits. And also a useful mission means a mission that can attain 1 or more objectives. So looking at the graphic, again, we'll talk about these trajectory terms later. But the nominal trajectory is the trajectory that the operator plans to fly. That's surrounded by normal trajectory bounds, which include random uncertainties such as effects of winds, guidance and performance uncertainty, etc. Those are usually fairly close to the nominal trajectory. But then you also have these limits of a useful mission, which is the operator indicating where they would like to be able to fly without flight abort, because the mission is still useful to them if they do fly in this direction, even though that's not the direction that they intended to fly in. So this is a simple example. This is just showing flight azimuth limits of a useful mission. But there could be other examples as well that characterize other types of failures. Next slide, please. Okay, section 450.108C covers flight safety limits objectives. And C1 states that flight abort must be used to ensure compliance with the safety criteria of 450.101A and B. 450.101A and B include collective and individual risk, aircraft risk, and risk to critical assets for launch vehicles and re-entry vehicles. Note that the FAA plans to issue guidance on how to comply with the flight safety limits objectives in an advisory circular titled Flight Abort Rule Development, planned for issuance in Q1 of next year. Next slide, please. Section C2 states that flight abort must be used to prevent continued flight from increasing risk in uncontrolled areas if the vehicle is unable to achieve a useful mission. Note that the regulation does not say preventing debris impacts, it says prevent increasing risk. This is because debris impacts are not the only risk contributors that must be accounted for. For example, a release of toxic propellants after an impact of a rocket stage must also be considered. And the term increasing risk is used instead of preventing hazards or preventing risk, because hazard containment may not be possible when the vehicle deviates from the limits of a useful mission. For example, during a period of overflight. In some cases, hazard containment will be possible. For example, if the vehicle deviates from the limits of a useful mission while over a broad ocean area and flies towards an uncontrolled area. While flight abort is sometimes no longer used during periods of downrange overflight, some periods of overflight are possible where flight abort is still used as a hazard control strategy. Next chart, please. Section C3 states that flight abort must be used to prevent the vehicle from entering a period of materially increased public exposure in uncontrolled areas, including before orbital insertion, if a critical vehicle parameter is outside its pre-established expected range or indicates an inability to complete flight within the limits of a useful mission. This performance-based requirement is similar to the traditional gate, where a decision is made whether to allow a vehicle to continue flight or to initiate flight abort before overflight of an uncontrolled area. Not all overflight would require this type of flight safety limit. It's intended for overflight of major land masses and large islands with substantial population, but not islands with small population or other areas of sparse population. It would also be required before orbital insertion because of the possibility of a random re-entry from a vehicle that cannot make a minimum safe orbit. A critical vehicle parameter is a parameter that demonstrates the vehicle is capable of completing safe flight through the upcoming phase of flight, for which population is exposed to hazardous debris effects from reasonably foreseeable failure modes. And we'd like to note that this regulation is flexible and that it does not prescribe the critical vehicle parameters to be used to judge whether flight abort is required. various parameters have been used for this determination historically. Next slide, please. Section C4 states that flight abort must be used to prevent conditional expected casualties greater than 1 × 10⁻² in uncontrolled areas due to flight abort or due to flight outside the limits of the useful mission from any reasonably foreseeable off-trajectory failure mode in any significant period of flight. So this regulation ensures that when flight safety limits cannot prevent hazards from affecting uncontrolled areas, the failure modes that result in deviations from the planned trajectory will not result in a high consequence event if the vehicle is unable to achieve a useful mission. This is possible when some public exposure must be accepted to allow useful missions to continue during a phase of flight when flight abort is still used as a hazard control strategy. An example of this is northeasterly missions launched from the Eastern Range that may overfly some portions of Canada on trajectories within the limits of the useful mission. If the vehicle fails after the overflight has begun and reaches flight safety limits protecting more westerly portions of the uncontrolled areas, the consequence from flight abort must meet the criteria in this section. Next chart, please. Section C5 states that flight abort must be used to prevent the vehicle state from reaching identified conditions that are anticipated to compromise the capability of the flight safety system if further flight has the potential to violate the flight safety limit. For example, if a certain roll rate would preclude ground-based flight abort commands from being received by the vehicle, a flight safety limit should be developed that triggers flight abort before the roll rate reaches this value. Next slide, please. Section C6 provides an option where in lieu of sections C2 and C4, flight abort would be used to prevent debris capable of causing a casualty due to any hazard from affecting uncontrolled areas using a flight safety system that complies with section 450.145. Section 450.145 describes the regulations for the highly reliable flight safety system. And section 2, which we just covered, is the requirement to initiate abort if it reduces risk in uncontrolled areas when the vehicle cannot achieve a useful mission. We also just discussed section C4, which is the requirement to initiate abort to prevent conditional expected casualties greater than 1E-2 in uncontrolled areas from flight abort or flight outside the limits of a useful mission. So what this regulation is saying is that flight safety limits meet the CEC requirements, even in the absence of a CEC analysis, if a highly reliable flight safety system is used to contain hazards. However, this strategy is not an option when hazard containment is not possible during a phase of flight when flight abort must be used as a hazard control strategy.
Hey,
For
Tom,
example,
interrupt you for a second. Would you mind trying to get a little bit closer to the microphone?
Certainly.
Thank you.
Yep, okay. I will also speak up a little bit. Okay, so again, this strategy is not an option when hazard containment is not possible during a phase of flight, when flight abort must be used as a hazard control strategy. For example, if an area of overflight occurs on a nominal trajectory during a phase of flight, when flight abort is still used as a hazard control strategy, an operator cannot claim containment during this phase and must meet sections C2 and C4. And an example means of compliance for this regulation are the legacy regulations in sections 213A, B, and D. Next slide, please. Okay, section D describes constraints of flight safety limits. D1 states that flight safety limits must account for temporal and geometric extents on the Earth's surface of any reasonably foreseeable vehicle hazards under all reasonably foreseeable conditions during normal and malfunctioning flights. And Section 2 says that flight safety limits must account for physics of hazard generation and transport, including uncertainty. So vehicle hazards include direct debris impacts, blast waves, toxic releases, etc., all of which must be considered when developing flight safety limits. And hazard generation and transport are factors that apply to all hazards, unlike factors that only apply to determining debris impact dispersions. Hazard generation refers to the process by which a vehicle becomes a hazard, and transport is how the hazard moves from the source to an exposed person or asset. Simply accounting for potential contributions to debris impact dispersions would not encompass all hazards, though debris impact dispersions also need to be accounted for under Section D2. And note that the AC planned for issuance in the first quarter of next year will also cover how to comply with the flight safety limits constraints. Next section, please. Section D3 says that flight safety limits must account for the potential to lose valid data necessary to evaluate the flight abort rules. So this is a performance-based regulation similar to the application of data loss flight times under Part 417, also known as green numbers. Flight abort obviously depends on the data used to judge whether abort is necessary. And the potential to lose track data is a contingency for which operators must plan. Note that data loss flight times may be an appropriate solution to account for the loss of track data, but that's not necessarily the only solution. This is a performance-based regulation. Next slide, please. Okay, Section D4 states that flight safety limits must account for the time delay, including uncertainties between the violation of a flight abort rule and the time when the flight safety system is expected to activate. This time delay is important because the decision to abort flight must be made in time to achieve the flight safety limits objectives, which is not possible unless the delay between the abort rule violation and flight safety system activation is known. Next slide, please. Section D5 states that flight safety limits must account in individual, collective, and conditional risk evaluations, both for proper functioning of the flight safety system and failure of the flight safety system. So risk analyses should be performed assuming the flight safety system works as intended, because the public should be safe given a deliberate safety intervention. And separately, the risk analyses should be performed considering the predicted reliability of the flight safety system. This reliability is important because even low probabilities of flight safety system failure can have significant impacts on risk. Next chart, please. Section D6 says that flight safety limits must be designed to avoid flight abort that results in increased collective risk to the public in uncontrolled areas compared to continued flight. This is a common sense requirement in that a safety intervention should not be riskier than allowing continued flight. And two methods of demonstrating compliance with this requirement are confirming that debris footprints from abort do not affect uncontrolled areas, which works best when inert debris footprints capture the hazard extent, and performing numerical analysis to show that the risk from each abort case is not larger than the risk from no abort. So in the graphic, the small fishhook shape is the island of Bermuda, and the red lines around it are example flight safety limits. Not the orange lines, that's a grid, but there are actually red lines among the blue ellipses. And the blue ellipses are debris footprints from many examples of flight abort action at the flight safety limits. So in this example, the margin between Bermuda and the debris footprints from flight abort is minimal and could be improved with modifications to the flight safety limits, because increasing the distance from the island to the flight safety limit will not expose additional uncontrolled areas in this example. So you really don't need to abort flight if it would endanger Bermuda, and allowing flight to continue a little further would ensure that Bermuda is safe. Next slide, please. Section D7 says that flight safety limits must ensure that any trajectory within the limits of a useful mission that is permitted to fly without abort would meet the collective risk criteria of 450.101A1 or B1 when analyzed as if it were the planned mission in accordance with section 450.213B2. So think back to the chart that we showed on limits of a useful mission and how they can include flights outside of where the operator is intending to fly. So this requirement is necessary because limits of a useful mission may be very expansive. For an example, an operator may want to be able to fly a wide range of unplanned flight azimuths on any particular mission if the vehicle were to fail to fly the intended azimuth. In cases like these, the decision to abort a flight before overflight should not be based on the pre-flight risk analysis for the planned trajectory, which likely assumes a low probability of flying an incorrect azimuth. When deciding whether a vehicle should be allowed to endanger populated areas in order to proceed on a useful mission, the assumption should be made that the vehicle is flying the trajectory that will create that public exposure, even though it may be an unlikely scenario. Therefore, this requirement results in analyzing the collective risk, assuming the vehicle flies the trajectory within the limits of a useful mission that's being considered for either a continued flight or flight abort. This requirement can result in some flight azimuths that are allowed to continue flight over populated areas, and some that are aborted before the overflight would begin, depending on the collective risks posed by those trajectories. Next section, please. Section E is related to the end of the use of flight abort as a hazard control strategy to protect against high consequence events. It states that a flight does not need to be aborted to protect against high consequence events in uncontrolled areas, beginning immediately after critical vehicle parameters are validated, if the vehicle is able to achieve a useful mission and the following conditions are met for the remainder of flight. First, flight abort would not materially decrease the risk from a high consequence event. And second, there are no key flight safety events. As an example application of this regulation, many orbital missions have a period of downrange overflight where flight abort would no longer protect against high consequence events. And the flight safety system is commonly safed before these periods begin, meaning that flight abort would not be used during the overflight period. We already talked about critical vehicle parameters on the chart for section C3. And a key flight safety event includes events that could compromise any safety critical system or otherwise increase the risk from high consequence events, such as events that subject a safety critical system to environments at or near the maximum predicted environment. Next slide, please. Section F contains requirements for flight abort rules, which govern how the flight safety limits are used. Section 1 says that vehicle data required to evaluate flight abort rules must be available to the flight safety system under all reasonably foreseeable conditions during normal and malfunctioning flight. The phrase "under all reasonably foreseeable conditions" acknowledges that some conditions that prevent vehicle data from being available to evaluate flight abort rules might be unforeseeable and therefore unpreventable through planning and design. Section 2 says the flight safety system must abort flight when valid real-time data indicate the vehicle has violated any flight safety limit developed in accordance with this section. When the vehicle state approaches identified conditions that are anticipated to compromise the capability of the flight safety system and further flight has the potential to violate a flight safety limit, and in accordance with methods used to satisfy D3 of this section, if track data is invalid and further flight has the potential to violate a flight safety limit. So section D3 is where the operator has to plan for the potential to lose track data. Next slide, please. Okay, section G contains the application requirements for flight abort. Starts with a description of the methods used to demonstrate compliance with 450-108C, which is the flight safety limits objectives, including descriptions of how each analysis constraint in 450-108B is satisfied in accordance with section 450.115, which is flight safety analysis methods. Also requires a description of how each flight safety limit and flight abort rule is evaluated and implemented during vehicle flight, including the quantitative criteria that will be used, a description of any critical parameters and how the values required in paragraphs C3 and E are identified. Also, a graphic depiction or series of depictions of flight safety limits for a representative mission together with the launch or landing point, all uncontrolled area boundaries, the nominal trajectory, extensive normal flight, and limits of the useful mission trajectories, with all trajectories in the same projection as each of the flight safety limits, and a description of the vehicle data that will be available to evaluate flight abort rules under all reasonably foreseeable conditions during normal and malfunctioning flight. Note that the application only needs to contain flight safety limits for a representative mission. However, any updates for any particular mission must be submitted no less than 30 days before flight, unless the administrator agrees to a different time frame. Next slide, please.
Okay, so we're going to go ahead and start this Q&A session. First up, we have a question from on would it be possible to give a brief recap on how the rules being presented differ from what is proposed? This would be particularly helpful for CEC and flight abort rules. So I think at a very brief level, we can probably do that, but the focus of this workshop is really teaching what is in the Part 450 and less about comparing it to the preamble of the NPRM. So we'll respond in writing to that question more thoroughly. And what we'll do is for CEC, the big difference for them was that CEC was very much prescribed. Also, Paul Watt, if you wanted to join us on the Q&A, you're welcome to join us, or Randy. But for CEC, it was very prescribed that you had to use a CEC method. Going from the NPRM to the final rule, we changed it to a high consequence event protection, and we allowed an alternative method besides using CEC as a measure of high consequence protection. And we also had some other ways, if you're already doing using a flight abort system, then you don't necessarily have to calculate CEC. And also, if you have demonstrated reliability for a phase of flight, you don't need to. So there was a number of changes from the proposed rule. On flight abort, they have essentially most of the regulatory changes are the same, just reorganized to be a little bit more efficient. Is there anything that Paul or Tom, you guys wanted to add to that? But we will respond in writing to that.
Nothing to add.
Capture, Michelle.
Okay. The next question is, if an operator meets conditional E sub C through alternative means, does that mean an FSS is not required per part 450, 143, and 450, 145, and an operator can use alternative means for meeting the remaining flight safety criteria, expected casualty, probability of casualty, in 450, 101?
Tom, you want to take that?
Sure. Thanks, Paul. So if an operator, if an operator has CEC below 1E-3, then they already meet the requirements for high consequence event protection. So there are ways, if they're over 1E-3, to satisfy the requirement. One is through the use of flight abort. Another is demonstrated reliability, which we discussed yesterday, which could apply to some phases of flight if that phase of flight has such reliability that we agree that that reliability alone is sufficient high consequence event protection. Also, there's alternative measures to CEC for high consequence event protection. So there are options there too. I think that we might want to reserve any further answers for a more detailed discussion offline.
Okay, thanks. When you use the term any trajectory, can any trajectory make this requirement incredibly burdensome? Does FAA have specific requirements in mind to better define the trajectory cases that should be analyzed in this manner?
Okay, so that's clearly in reference to the requirement to analyze any trajectory within the limits of the useful mission to see if it meets the collective risk. And yes, we realize that analyzing every trajectory in that span would be burdensome. In the advisory circular, we have a method for satisfying the requirements that would not require the applicant to analyze every trajectory within that span. We'll refer you to that advisory circular, please.
Okay, thanks, Tom. Is the intent of this requirement to allow overflight in the event that an on-trajectory explosion or loss of thrust is considered a high consequence event?
Okay, I believe that's in reference to section E, which is related to the end of flight abort. So yes, that's one application. So that's where we acknowledge that some high consequence events are possible when the flight safety system would no longer be effective. And downrange overflight is the best example of that in current practice. Okay,
thank you. How does this requirement, 450-108F2, differ from 450-108C5? Can separate examples of each requirement be provided? And I'm pulling up my reg here to help you with
okay,
what is in. So 108F2 is the requirement, the flight abort rule, where it says the flight safety system must abort with valid real-time data indicates, et cetera, and then 108C5 is the requirement, let's see, flight safety limit objective number 5 to prevent the vehicle state from reaching identified conditions that are anticipated to compromise the capability of the flight safety system if further flight has the potential to violate a flight safety limit. I guess what's the difference between those two?
Sure. So one is a flight safety limit and the other is a flight abort rule. They are related, but they're not trying to make you do two different things really. So essentially the flight abort rules are the list of rules that either say a range safety officer or maybe an autonomous system follows, and the flight safety limits are the parameters associated with those rules. For example, you might have a flight abort rule that says you have to abort the flight if the roll rate reaches X degrees per second. And then that would be an example from F2. And then from C5, you would say the flight safety limit is 10 degrees per second. So they work together. Again, you may have flight abort rules that are common across a vehicle for a number of flights and refer to flight safety limits that can vary from mission to mission.
That's a great question and great answer. Thank you. We've had two questions come in that are very similar, so we're going to try to combine them here. 450-213 states flight abort products need to be provided no less than 30 days before flight. If launch is occurring from an FAA-approved range and some products do not end up being within that 30-day constraint, is that a license violation? And is a waiver needed if known in advance?
So I think, Michelle, if you don't want to try to field that one, I think I'm going to defer that one to later discussion.
I will. I think I'm not sure we actually have a lot of charts on this because it's technically not part of 450, but we modified part 404, I believe it is, for the filing petition of waiver. So if you needed a waiver, the way that it worked before was that a petition for waiver had to be submitted at least 60 days in advance. And now when there's a petition for waiver, the new 404.5, there is some guidance there that that you can seek relief and within a timely manner.
Yeah, I think the bottom line there is, we'll work with the applicant during the application process to enable alternative timeframes.
Yep. But we'll go ahead and take a closer look at that and respond in writing. Okay. Let's see. I think there was a second part to that, but I will go on. Will the regulations be expanded to include flight abort in case of extreme hazard for manned missions? If there's a risk of injuring 3 to 4 people on the ground versus 5 people in the spacecraft, what is the advised decision process? So Paul, I was wondering if you could take this one.
Sure. Well, so we're not here today to talk about future regulations, but Part 450 does work together with Part 460 in terms of human space flight. As I mentioned yesterday, the fundamental criteria for when a flight abort is necessary to protect public safety is independent of whether or not there are humans on board.
Okay, and I realize I just misspoke on the waivers. It's the alternative timeframes that don't have that has that timeliness requirement in it, not the waivers. Okay, so we're waiting for some more questions to come in. We don't have any more in the queue right now. So we'll wait a few seconds for that. And if we don't have any more questions, we will, to stay on schedule, we'll go ahead and give folks another break and start the next hazard control strategy flight hazard analysis at the scheduled time. But there are some more questions coming in. So let our team just work those for a second to get those to us. And just as a reminder, we will be responding to all the questions more in depth. I think yesterday we did speak to the caveat that during these Q&A sessions when we're giving verbal answers, we're kind of thinking on our feet, and this rule is new to all of us. So we will be responding in writing to all the questions and posting those to our website. And I think, one thing to note, to follow on with what Paul said, Part 460 is our human spaceflight regulation. So for any crewed vehicle, you would have to follow Part 450 and Part 460 together.
So, Michelle, I'm seeing there is another question.
Yeah, it's not in our queue yet, though. But go ahead if you want to go ahead and.
Yeah, there's a question. Are there no criteria in 450? Oh, it just popped away.
Okay.
Okay, coming up.
So there are no criteria in Part 450 for the safety of people on board, be it crew or passengers. And I think that's what I was just speaking to a little bit, that it's almost like a modular approach. And Part 460 has always been a separate set of regulations, whether you were adding it on to Part 431 for an RLV or for 435 for a reentry vehicle. And that continues to be the case. Part 460 is still in the CFR. It will not be removed in 5 years. It's not a legacy regulation. That's a current regulation. And it will still be something that you would have to, Part 450 mentions if you have humans on board, you have to comply with Part 460 in addition to Part 450. And I believe that's mentioned in 450.45, I believe, that has the requirements for human spaceflight.
Michelle, I think we have a follow-up on that.
Okay, is Part 460 going to be integrated and streamlined the same way 450 is? So we are working with ComStack to prioritize our rulemaking agenda going forward. So we're waiting for some guidance from industry on to prioritize our rulemaking efforts.
I don't see any other incoming questions.
I don't either. So I would encourage folks to, type the questions as the speakers are speaking so that we can have them all queued up. And we really do encourage, as much interaction as we can during this virtual format. As I think I mentioned yesterday, but for anybody who's new for day 2, we wish we could have this in a conference room where we could all be together and have a large amount of interaction. But this is the format we have. And I think the best way would be to just keep the questions coming as you think of them while the speaker is speaking, so that our team who is gathering the Q&As and feeding them to the speakers can have those ready for the Q&A session. That would be great. But if we don't have any more, we're going to go ahead and break, and we'll be back with flight hazard analysis at 11:06. So it'll give you a chance to have a nice break. All right. Thank you, everyone. Hello, everyone. I want to bring everyone back. We're going to be starting here. Just as a reminder, we've just started into our 4 hazard controls. Mr. Tom Ricketson just briefed our flight abort section. And next up, we have the flight hazard analysis. And for that, I'm going to introduce Mr. Christopher Vance.
Good morning. I'm going to be covering actually 450.109 flight hazard analysis, 450.110 physical containment, and 450.111 when waiting. But first, I'll discuss 450.109. 450.109A applicability. 450.109 applies to the use of a flight hazard analysis as a hazard control strategy to derive hazard control for the flight or phase of flight of a launch or reentry vehicle. In addition, computing systems and software associated with hazards are addressed by 450.141. A flight hazard analysis must identify, describe, and analyze all reasonably foreseeable hazards to public safety resulting from the flight of a launch or reentry vehicle, mitigate hazards as appropriate, and validate and verify the hazard mitigations. AC 450.109-1, planned for Q1 2021, will provide compliance guidance. Next slide. (450.109B) analysis. Flight hazard analysis is a traditional safety approach for RLVs and is the most flexible hazard control strategy because it allows for deriving specific hazard controls unique to the launch or reentry system and operations concept. Flight hazard analysis is mandated as a hazard control strategy if the other hazard control strategies cannot mitigate the public safety hazards sufficient to meet the safety criteria of 450.101. Each flight hazard analysis must, B1, identify all reasonably foreseeable hazards associated with the launch or reentry system relevant to public safety, including those resulting from I through IX listed here. B2, assess each hazard's likelihood and severity. B3, ensure that the likelihood of any hazardous condition that may cause death or serious injury to the public is extremely remote. B4, identify and describe the risk elimination and mitigation measures required to satisfy B3 above. B5, document that the risk elimination and mitigation measures achieve the risk levels of B3 above through validation and verification. Verification includes analysis, test, demonstration, or inspection. Next slide. 450.109C, new hazards. Criteria and techniques for identifying new hazards throughout the life cycle of the launch or reentry system must be established and documented. 450.109D, completeness prior to flight. For every launch or reentry, the flight hazard analysis must be complete and all hazards must be mitigated to the acceptable level of B3. 450.109E, updates. An operator must continually update the flight hazard analysis throughout the life cycle of the launch or reentry system. And 450.109F, application requirements. An applicant must, F1, submit flight hazard analysis products of paragraphs B1 through 5, including data that verifies the risk elimination and mitigation measures required by paragraph B5, and F2, the criteria and techniques for identifying new hazards throughout the life cycle as required in paragraph C. Next slide. So for guidance on a flight hazard analysis, we're going to discuss the flow. So if you follow the requirements in the flow of a flight hazard analysis, you start with B1, identify hazards with traceability, go to assess severity and initial likelihood, check compliance with acceptable criteria, identify mitigations with traceability at the appropriate level, identify verifications with traceability to mitigations, validate mitigations and verifications, validate compliance with acceptable criteria, continuously update and capture any new hazards, ensure completeness prior to each flight. Next slide. This is an example structure of a flight hazard analysis. It begins on the left with data from the functional hazard analysis and then decomposes further to possible causes of those functional failures. This is done via flight fault tree analysis, FMEA, subsystem hazard analysis, or other appropriate analysis. Then it moves into identifying and verifying mitigations to specific causes of functional failures at the subsystem and component level. That is then moved on to identifying and verifying specific system mission mitigations for residual system safety risk of public safety hazards. All of this is to ensure traceability from the functional hazard analysis through to the final mitigation and risk assessment at the system and mission level to achieve the requirements of B3. Next slide. 450.110, physical containment. A, applicability. This section applies to the use of physical containment as a hazard control strategy for the flight or phase of flight of a launch or reentry vehicle to meet the public safety criteria of 450.101. AC 450.110-1 planned for Q2 2021 will provide compliance guidance. 450.110b, containment. To use physical containment as a hazard control strategy, an operator must, B1, develop the flight hazard area in accordance with 450.110.133, B2, ensure that the launch vehicle does not have sufficient energy for any hazards associated with its flight to reach outside the flight hazard area. B3, ensure the hazard area is clear of the public and critical assets. And B4, apply other mitigation measures necessary to ensure no public or critical asset exposure to hazards. Next slide. 450.110c, application requirements. This hazard control strategy is appropriate for missions that have limited vehicle kinematic range and have tightly controlled airspace and access to the operational area. An applicant must submit C1, a demonstration that the launch vehicle does not have sufficient energy for any hazards associated with its flight to reach outside the flight hazard area developed in accordance with 450.133. And C2, a description of the methods used to ensure that the flight hazard areas are cleared of the public and critical assets. Next slide. 450.111, wind weighting. A, applicability. This section applies to the use of wind weighting as a hazard control strategy for the flight of an unguided suborbital launch vehicle to meet the public safety criteria of 450.101 A, B, and C. 415.109B2, 417.125, 417.201C, and 417.233 and Appendix C to Part 417 provide relevant compliance guidance. For the flight of an unguided suborbital launch vehicle that uses a wind weighting safety system, B1, the launcher azimuth and elevation settings must be wind weighted to correct for the effects of wind conditions at the time of flight to provide impact locations that will ensure compliance with the safety criteria of 450.101. And B2, an operator must use launcher azimuth and elevation angle settings that ensures the rocket will not fly in an unintended direction, accounting for uncertainties in vehicle and launcher design and manufacturing and atmospheric uncertainties. Next slide. 450.111c, analysis. An operator must, C1, establish flight commit criteria and other flight safety rules that control the risks to the public from potential adverse effects resulting from normal and malfunctioning flight. C2, establish any wind conditions under which flight may occur. And C3, conduct a wind weighting analysis that establishes the launcher azimuth and elevation settings. 450.111d, stability. An unguided suborbital launch vehicle in all configurations must be stable throughout each stage of powered flight. 450.111e, application requirements. An applicant must submit E1, a description of its wind weighting analysis methods, E2, a description of its wind weighting safety system, and E3, a representative wind weighting analysis using actual or statistical winds for the launch area and samples of the output. Next slide.
Okay, thank you, Christopher. So Christopher covered the remaining 3 hazard control strategies. If there's any questions on flight hazard analysis, wind weighting, or physical containment, I know we've got some of our system safety folks. I've looked through the participant list. Please ask your questions and we will go through them. And our queue is clear right now, so please submit your questions. All right. Okay. I think you all want a longer lunch break. So we will just wait patiently, give folks a few minutes to type the questions in. Okay, well, we'll give it like another minute to see if folks have questions. But otherwise, we don't have any more sessions planned until we come back from lunch. At that point in time, we will have covered all of our hazard control strategies, and then we'll go into the flight safety analysis. One note that I think that's really unique about 450, and it goes to how we combined the ELV regulations and the RLV regulations, is this hazard control strategy. It lets folks, fly the way that they've been flying using, the ELVs have traditionally used flight abort, the RLVs and reentry vehicles have traditionally used flight hazard analysis, and that is preserved under one rule, and that's done through our hazard control strategies. I don't see any other questions, so I think we will go ahead and wrap for the morning. The time to come back is 12:10 Eastern Standard Time, and this afternoon is really packed full of flight safety analysis, so hopefully we'll see you all back for that at 12:10. Thanks, everyone. Okay, I'd like to welcome everyone back. We are going to be starting our session on flight safety analysis. And I want to remind folks to please keep the questions coming in so that we have them all queued up for the Q&A session. We expect that this session on flight safety analysis, scope, and methods could go for about 40 minutes, and then we'll have our Q&A at 12:50. Thank you. Over to you, Paul.
Good afternoon, everybody. It's a pleasure for me to present on the flight safety analysis, scope, and methods requirements. But before we dive into those specific requirements, let's put the flight safety analysis in some context. So first slide. The first a flow diagram that's taken from the Range Commanders Council RCC 321.20 standard, and it shows the overall risk management process that flight safety analysis is a key part of. So risk management is a systematic and logical process to identify hazards and control the risks they pose. So starting at the upper left slot of this figure, you see the first phase is the mission definition and the hazard identification. In the context of Part 450, Section 450.213 with pre-flight reporting is an example of mission definition, and 450.107 coming out of phase one, we should have an understanding of the hazards and an initial mission plan. Phase two is the risk assessment phase, where we perform analyses to quantify the risks posed and understand the risk drivers, such as a particular failure mode in a given phase of flight. So sections 450, 135, 137, and 139 are examples of quantitative risk assessments. In phase three, the risks are compared to acceptable criteria, which is 450.101, and we talked at some length yesterday. If the 101 criteria is not met, or if the mission could be modified to mitigate those risks consistent with the mission objectives, then there's a path back to phase one. An example would be the identification of flight safety limits that are necessary to comply with 450-108. Phase 4, from an FAA perspective, involves more than just risk acceptance. In Phase 4, the operator must perform post-flight analysis and report anomalies that are material to public safety in accordance with 450-103 Delta and 450.215. Incorporating any corrective actions is an example of lessons learned for future flights. Next slide, please. So this slide is a roadmap of the flight safety analysis as a whole. A flight safety analysis consists of quantitative analyses that are used to, number one, demonstrate compliance with the safety criteria we saw yesterday in 450-101, to determine flight hazard areas and other mitigation measures, to determine flight commit criteria and flight abort rules if necessary. So sections 113 and 115 contain the flight safety analysis scope and method requirements. And 117 through 139 fit into these two categories. Analyses that are used to develop key inputs to the quantitative risk analyses, such as the probability of failure analysis, trajectory analysis for normal flight, trajectory analysis for malfunction flight, the debris analysis where we characterize the debris that would be resulting, for example, from an on-trajectory explosion, but also any nominally generated debris. Population exposure analysis is another key input to the quantitative risk analyses. The other category is the quantitative risk analyses themselves that demonstrate compliance with 450-101. So there we have the flight hazard area analysis, debris risk analysis, the far field overpressure effects analysis, and the toxic hazard analysis. So an example of a failure mode would of course be an on-trajectory explosion, which would be different than a non-trajectory loss of thrust. You could have a control failure that causes a departure from the normal flight envelope, also known as malfunction turns. And the AC 450-101-1 in section 8.3 describes a fairly comprehensive generic set of failure modes, but of course each vehicle could have unique failure modes. Next slide, please. So this is a slide that provides an overview of the entire debris risk analysis process. So in one slide, we graphically see all the various steps that go into producing, for example, an estimate of the expected casualties. So starting on the upper left, you define your failure modes, such as what I just mentioned. Then you define the failure rates for each of those failure modes. So the probability of failure in a given second of time, for example, that you would suffer a loss of thrust or an on-trajectory explosion. Then you define the dynamics of the vehicle dispersions, which we'll explain in a little more detail in a few minutes. You have to include the effects of the debris dispersions, and we'll also go into those. But in a nutshell, if you look at this little figure on the lower left, the idea is the rocket launches, it gets up to a certain point in flight. There's, in this case, an explosion, and then you'd have the debris falling, and it would fall in these different locations. And there's different probabilities of these different categories of debris falling in those locations. So we compute those impact probability distributions for each object, and for each population center, then you can estimate the probability that a given population center would be impacted. The next step then is to compute the casualty expectation for each population center, for each class of debris for each failure mode for each time in flight, and then of course combine those casualty expectations and sum for the total collective risk. Next slide, please. So this next slide shows the key elements of a flight safety analysis. It's just what we talked about, but broken down. You can see a little more detail on those component parts. So starting in the upper left, the probability of failure analysis, the requirements on 450-131. So here we quantify the probability of debris events, some of which could be intentional, like jettisoning a stage or a payload fairing. Others could be the result of a failure. And those probabilities have to be allocated to each failure mode and flight time. The next major box there involves characterizing the trajectories. And we have two different flavors to that. The normal trajectories, so if the vehicle performs as expected, versus malfunction turns or malfunction trajectories where the vehicle departs from normal flight. And the main output there we're looking for is breakup state vectors for each time in flight and for each failure mode. The box on the upper right refers to the debris list or the debris analysis, as we call it in 450-121. So here, the object is to develop a quantitative description of the debris that would be generated, and that would likely be different if you had, for example, an on-trajectory explosion compared to an aerodynamic breakup or other sources of breakup. Part of that generally involves grouping the debris into similar fragments that can be treated as a group, as depicted on some of the slides that we'll see in a minute. After you've characterized that debris, then the analysis proceeds to the lower right, and you would characterize the debris impact dispersions. So now the output is a probability distribution for the dispersion of each category of debris given each breakup state vector. A breakup state vector is the position and velocity at the time that a debris event occurs. So in the middle, on the bottom row, we have the impact probability. So in sections 450-133 and 450-135, the probability of an impact on a protected asset is computed. So for example, the probability of impacting on a critical asset, the probability of impacting on an aircraft, the probability of impacting on a populated area. So each of those needs to be quantified. But just because you have an impact doesn't mean that you have a consequence that would result in a casualty or loss of functionality for a critical asset. And so on the last box on the lower left, the analysis looks at the vulnerability. So I've got a given piece of debris impacting, for example, a certain kinetic energy on either a person outdoors or somebody in sheltering, and their vulnerability, of course, would be different depending on the nature of their sheltering. So those last two blocks on the lower left, the vulnerability, the impact probability, and the criteria for aircraft protection has some aspects that are unique to aircraft hazard analyses because, of course, the aircraft's velocity contributes greatly to the nature of any collision. Otherwise, the submodels that are depicted here are common with the ground risk analysis. Next slide, please. So this slide shows an overview of all the inputs and outputs for a flight safety analysis, and you can see that there are many. So starting on the upper left, we see there's some site-specific data that's marked in light green. So for example, part 451.23 describes the population sheltering database, or requirements that are necessary to describe the population and sheltering in the vicinity of where debris could impact. We'd also have structure cost database that's important to us for computing the MPL. This also could be specifics about critical assets in the area. You would also have wind with uncertainties that are characterized in a particular location. So that's part of the requirements in 450.121. We could have unique features in terms of aircraft flying in that vicinity. So for example, out over the broad ocean areas, we don't expect general aviation aircraft, at least not of a certain type. We expect perhaps business jets, but not a Cessna or typical small aircraft like that. So we also have vehicle-specific data that's necessary, and that's shown colored in light purple. So starting on the upper left, you see the trajectory data, requirements in 417 or 450, 117, and 119 to characterize the normal trajectories, including those uncertainties and possible malfunction trajectories as well. The vehicle data would also include, the specifics of the design of the vehicle as depicted, with drawings and analysis as required by 450.45. So the light blue refers to data that would be derived for a specific scenario. So for example, the failure probability over here on the right-hand side, which is a subject of 450.131, is one of the key inputs there would be the flight history for vehicles that were developed and launched under similar circumstances, as well as perhaps some environmental factors that could influence that. And from there, we develop a vehicle failure event tree, different types of failure modes and their probabilities. Also from the vehicle data and the history, we're going to be developing the breakup debris lists that are the subject of 450.121. Coming out of the trajectory analysis, we need to perform abort and malfunction trajectory modeling, and then account for the flight safety abort criteria to determine where the breakup state vectors could be and the uncertainties associated with those. So you can see there's a great deal of input data of these various flavors that then goes into the quantitative risk assessments that are required under 450.133 and 135, and various risk measures as required by 450.101, such as the individual risk and collective risk. And that outputs typically include contours with different probabilities of casualties and different probability of impact. Next slide, please. So this slide shows the debris footprint concept, and we have a few other slides to give people a better feel for what a debris footprint is. But in its most fundamental form, the debris footprint's a statistical description of the debris scatter that could result from a breakup at a specific point in time and space. So the footprint is essentially a statistical representation of an accident. It might not necessarily be an accident. It could be just the nominal jettisoning of a stage also can result in a footprint. Sometimes stages jettisoned, especially later in flight, will tend to break up, subsequent to jettison. So we'll see a little more about the debris footprint on the next couple of slides. Okay, so this slide introduces some of the physics involved in a debris footprint, including the concept of a debris center line and the ballistic coefficient, which is denoted by the Greek letter beta. So you'll hear us talking about betas. So basically, if you look, starting at the launch point, we have a line depicting the flight of a vehicle, let's say nominal flight of a vehicle up to the point where there's a breakup. An easy one to think of is just an on-trajectory explosion. So from there, we're going to have debris, and the debris paths then are computed based on Newton's laws of motion. And we have, an ideal and hypothetical case where we have no drag, no atmosphere, for example. Maybe you're launching from the moon. But you could, the debris would then fall here at this point marked by the vacuum impact point. So very high ballistic coefficient debris is going to land close to that vacuum impact point. Okay. And you see that as you decrease the ballistic coefficient, the debris gets more and more affected by the winds. So basically, the ballistic coefficient is a ratio of the weight and drag forces. You see the formula there. And so when you have a very low ballistic coefficient, the debris slows down very rapidly, right, by drag. And then it would essentially get blown by the wind in the direction of the wind. So you see this debris center line is ideally joining the center points of those dispersions that we're going to see on the next slide. So in this case, the wind is purely cross range, and this is not, this is of course not always the case, but it is typical. For example, as we'll see on this next slide. So here's our exciting movie. I asked to stop at 30 seconds. Okay. So what you see here is a depiction of a footprint. This is a launch of an ELV and from Vandenberg. And you see the footprint. Can you go back to that slide? Okay. Thank you. Okay, stop around 30 seconds. Doesn't have to be exact. All right, so you see the rocket, flying up, essentially starts off going straight. If the rocket were to explode at this time, then these ellipses depict, a confidence of containment of debris of different ballistic coefficients generally, but also perhaps different induced velocities. So we have the debris footprint starts off very typically as looking like circles. Okay, can you roll forward to 60 or 90 seconds? All right, so we see the footprint, evolving. Stop at 90 seconds, please. So the footprint's evolving, hopefully looking similar to the debris center line illustration that we had on the previous slide. What you see is these yellow ellipses are depicting debris with lower ballistic coefficients. It doesn't have to be exactly 90 seconds. You can stop at 80 seconds, is fine. Okay. All right, thank you. One of the points I wanted to make here, you see that, the path of the vehicle on the ground is its present position projected onto the surface of the Earth. And you see that by this time, around 90 seconds, really no debris would be predicted to impact directly below the vehicle. Right? The vehicles pick up enough velocity that the high ballistic coefficient debris is well out in front, and the low ballistic coefficient debris would be blown, in this case, cross range and away from the present position of the vehicle. Could you get it to play out to close to 120? There you go. Stop. Thank you. So the point to notice here is the debris footprint is now almost entirely downrange, and these high ballistic coefficient debris that are shown in red and orange are well downrange, and this effect will increase as time progresses, such that it's not typical that where the debris could land could be thousands of miles downrange from the present position of the vehicle as the vehicle approaches orbital insertion. So hopefully that gives you a feel for a debris footprint and how it evolves during a typical ELV flight. Okay, very good, thank you. So we can go to the next slide, please. So this slide is an illustration of the typical sources of debris impact dispersion. I've mentioned a couple, such as the wind and the effects with drag. So again, we have this depiction. The vehicle launches, gets up to a certain point in flight. There's a breakup, could be on trajectory explosion, on trajectory aerodynamic breakup. There's going to be some uncertainty in the position of the vehicle and the velocity of the vehicle at a given time in flight. Even if it's behaving nominally, there's normal dispersions based on the performance of the rocket or perhaps the winds affecting the rocket itself. Other key contributions, you see the velocity perturbation due to destruct. So if there was, intentional flight termination action taken, or if the vehicle, simply blew up on trajectory, we would expect that there would be induced velocities, that the explosion would propel those pieces and change the velocity of certain pieces, from what the velocity of the vehicle was at the time of the breakup. So in addition to the drag dispersion uncertainty, because these are highly irregular pieces, of course, and it's very difficult to predict their ballistic coefficient with great certainty. So we're going to have some contribution to the impact probability dispersion due to our inability to predict the ballistic coefficient with great accuracy. In addition, there's lift effects. Lift effects were, in fact, very prominent, the dominant source of cross-range dispersion in the case of the Columbia accident, because the winds were more or less parallel to the downrange direction. We had small velocity perturbations due to that, hypersonic aerodynamic breakup. And so what was left was really the lift effects. So these uncertainties can be accounted for using statistical methods that could be either analytical or Monte Carlo sampling, but we account for all those, and it's basically just Isaac Newton's laws. And we can then compute an impact probability distribution as shown here. They're often bivariate normal. They don't have to be bivariate normal, but it's very typical based on the central limit theorem when you have multiple sources of uncertainty to get normal distributions. Okay, next slide, please. Okay, so this slide shows the regulation text for 451.13 on the scope of the flight safety analysis requirements. And you can see, for example, that the flight safety analysis for launch must cover all phases of flight from liftoff to orbital insertion. And that, of course, aligns perfectly with the safety criteria in 451.01. You see these other scopes depending on the type of operation, if it's a suborbital launch, a disposal, or reentry, as we discussed yesterday. So the flight safety analysis must cover all phases of flight during these periods for those different types of operations. In AC 460.101, section 6.1, there's a description of what we mean by phase of flight. And I'll just leave that there for you to read. So paragraph B provides some flexibility in that, as noted in the preamble to the final rule, a flight safety analysis is not required if an operator demonstrates reliability by using operational and flight history to show compliance with the risk criteria. So an example of that would be the L-1011 carrying the Pegasus vehicle, where there was plenty of previous flights that, just from empirical data alone, you could see that the flight of the L-1011 would meet our risk criteria in 101A and B. There's a note also in the preamble to the final rule about what operational history includes. And so you can see that. The other point that I wanted to make here about carrier aircraft is, of course, another part of the rule requires that any attachment of the rocket to the carrier aircraft, you'd have to use system safety practices to demonstrate that the probability, for example, of an inadvertent release is extremely remote. So any hazard that would be unique to the fact that there's a rocket attached to this aircraft, you need to demonstrate that those hazards are extremely remote in order to use that operational flight history. Okay, next slide, please.
And Paul, just a quick time check. We're at the time for Q&A, and I think you have about 3 more charts left.
Okay, I'll pick up the pace. So the next slide shows the regulation in the 450.115 showing the scope and fidelity of the flight safety analysis. So the scope is that the flight safety analysis must account for all reasonably foreseeable events and failures of safety critical systems during nominal and non-nominal launch or reentry that could jeopardize public safety. So 450 does not direct how an operator must identify reasonably foreseeable events or failure modes. But 103B does direct that a functional hazard analysis must be done. The paragraph B shows the requirements for the flight safety analysis level of fidelity. And the fundamental requirement here is that the analysis must have a level of fidelity that's sufficient to demonstrate that the risks satisfy the safety criteria in 101. including use of any mitigations, such as the flight abort, but also accounting for all known sources of uncertainty using a means of compliance accepted by the administrator. And as we talked about yesterday, another important purpose and requirement for the flight safety analysis is to identify the dominant source of each type of public risk in terms of phase of flight. So it could be, an on-trajectory explosion leads to a debris hazard, or something along those lines. Okay, we can go to the next slide. So this next slide shows the application requirements. So these application requirements for the flight safety analysis methods apply to all the flight safety analysis sections. So, the applicant needs to identify everything that's listed here. I've highlighted the rationale for the level of fidelity. So the rationale for the level of fidelity is typically linked to those requirements that we just saw in B1 about accounting for all known sources of uncertainty and also producing results that are consistent with or more conservative than the results available from previous mishaps, tests, or other valid benchmarks, such as higher fidelity methods as required by 450-101G. We have one last slide. So this slide is a conceptual plot that's intended to illustrate how uncertainties and conservative assumptions influence the required level of fidelity for flight safety analysis methods. So the plot shows increasing failure probability as you move up on the vertical axis and increasing consequences of a failure as you move to the left on the horizontal axis. So the acceptable limit, acceptable risk criteria, is this dashed line that goes off at an angle. And so the uncertainty in the expected casualties is depicted as an ellipse about a dot. The dot depicts the mean or point estimate for an EC. So as your results move closer to the acceptable limit, such as depicted in green, you should have smaller uncertainty than those with greater uncertainty, so the dark red. Now, that's assuming that your uncertainties are, that there's no bias in your uncertainties, whereas it's very typical to make conservative assumptions. Therefore, those conservative assumptions would move the point estimate to be at the top edge. For example, if you had a conservative failure probability estimate, your point estimate would be at the top edge of this ellipse. And if you have conservative estimates of the consequence, then the point estimate moves towards the left. So one last thing to mention, sorry. The explanation about the details about how to comply and discussion of different levels of fidelity analysis is available in these ACs. And I wanted to say that any resemblance between this figure and the Death Star is purely coincidental. Thanks. Over to you, Michelle.
The Death Star. Okay. Thank you, Paul. And actually, you kept us right on time, so that's perfect. And we have a good number of questions. So let's start the Q&A session. Is there anybody else going to be joining us? You can go ahead and turn on your cameras if any of the other SMEs are joining. The first question is there a standard tool for conducting debris risk analysis, or does FAA-AST perform that analysis?
So there are tools, various tools that are available. The U.S. government has a standard tool that the FAA, the Space Force, the NASA, we all use. It's available for use, if you contract with the contractor that keeps that tool. There are other tools that other operators have used very successfully. So there's a suite of tools that have been used. There's no one standard tool, though. We think that it's important to allow for innovation in this area, and we're not going to specify that you must use a particular tool.
Okay, great. In reference to AST's debris field propagation, what are the planned protections for aircraft flying in the NAS? Is it separation versus segregation?
So that's really more of an air traffic question. Our requirements are, of course, to define aircraft hazard areas, and those are areas where no aircraft should be present during the launch or reentry. Air traffic has been investigating different methods that would allow smaller hazard areas to be closed. In particular, coming out of the Columbia accident, we noticed that the debris took several minutes to reach altitudes where aircraft could be flying. And so post-Columbia, we had a system where aircraft could remain, performing normally as the shuttle flew over, but the FAA was on the line, getting real-time communication with NASA, such that in the event that the orbiter was lost, that planes could be cleared from the hazard area. So we're always, partnering with air traffic to minimize the impact on the national airspace to the greatest extent possible. But it's incredibly important. That's our #1 priority, to make sure that people in aircraft are sufficiently protected.
Great. This may be coming up, but is there guidance on how to identify or populate a debris catalog for a launch vehicle? For example, what types of components should be assumed to be fractured and how many pieces, etc.?
Yeah, there is guidance. Now, this is an area where I think we'll cover that better in the later section.
Okay. What, if any, are the significant changes to the flight safety analysis requirements of Part 450 relative to the legacy 415, 417 requirements?
So they're remarkably similar. We generalized the requirements and made them more performance-based. In the case of the probability of failure analysis section, 417 did not include a paragraph about the allocation of the probability of failure. So in between 417 and 450, a lot of work went on in the Common Standards Working Group to develop requirements for the allocation of the probability of failure, which we'll cover later today. That's probably the biggest change. We have explicit requirements, of course, now, as we just saw, to identify the dominant contribution to the risks and to explicitly understand those uncertainties. But those were always implicitly necessary, really, to do a good flight safety analysis.
Okay, our next question is about 450.113A3, which is the scope, and that's the flight safety analysis scope for disposal from the initiation of the deorbit through final impact. And the question is 450.113A3 also exempt if the disposal targets a broad ocean area?
Okay, so exempt is a big word in the regulatory sense. The short answer is no. You would need to do some sort of analysis to demonstrate that the debris would be contained within a broad ocean area. So for example, you'd need an understanding of your normal trajectory dispersions. Hopefully your failure probability would be less than 3%, which means that those malfunction trajectories would not be necessary to demonstrate compliance with the 97% confidence of containment.
Okay. Is the flight safety analysis needed for disposal of stage 2? Is an ellipse in the ocean with no land or population enough of analysis?
Yes, if that ellipse represents 97% confidence of containment.
Okay. Can the FAA give an example where an operator might use this requirement in a manner agreeable to the administrator?
Okay.
I believe that's that must be within the scope and methods section, I guess.
Okay. So I think that's probably a reference to
I think that's 113 Bravo is an operator is not required to perform or document a flight safety analysis for a phase of flight if agreed to by the administrator based on demonstrated reliability. So that's,
yeah.
I assume that's the agreed to by the administrator part of this.
Okay, sure. Yeah, the best example would be the Pegasus being carried by an L-1011. There was plenty of empirical data to show that, you know, the flight of the L-1011 met the risk criteria that's now in 450-101. And so it takes a lot of flights to demonstrate that, but you know, the L-1011 had some millions of flights, and only one person, as I recall, was ever injured on the ground. So that's different than the demonstrated reliability that we talked about yesterday in 450-101 Charlie. The 101 Charlie, as we saw, had to do with protection against high consequence events, and the criteria is tied to the CEC, or conditional expected casualties, as we saw yesterday. Whereas here, the criteria is compliance with the individual and collective risks in 450-101 Alpha and Bravo.
Okay, and I think that pretty much answers the next question, which was queued up, which was, what does demonstrated reliability mean in this context? And you just covered, you know, we use demonstrated reliability in two contexts, one in 450-101 and then one in 450-113, and you just covered both of those. So
yeah, I would just point out that there is you know, some statements in the preamble about what we consider to be operational history. I know there was some question about that, but it's there for everybody to read.
Yep. On operational history, is that component test, system test, and qualification? Are there requirement sets or test standards that provide baseline reliability? For example, RCC 319 with a 99.9% reliable at 95% confidence. Are there other standards that provide a reliability upon conformance? And the second part of that is, should they assign a reliability to SMC S016 and RCC 324? That was discussed at some point.
Okay, really good questions.
And that's our question in the queue right now, so you can take your time on that one.
Really good questions. Let me first say that when we're talking about demonstrated reliability, we're generally looking at the integrated system. And so operational flight history is the most important, is the gold standard. And I have that quote from the preamble. Operational history includes the flight time and or cycles of an aircraft, which may have an airworthiness certificate operating under Part 91 or 135 or 121 as an example. Flight history could be represented by flight time accumulated through a period of developmental flights and flight tests of a vehicle that does not have an airworthiness certificate. We're really looking at flights. Now, you know, in the case of the flight safety system, most people know that if you comply with RCC 319, then we consider that a demonstration of 3 nines at 95% confidence reliability. We do not have standards of, that would, for example, apply to a flight safety system under 450, 143 that assign a particular reliability level. That's something that we'd love to work with industry, to partner with industry to develop. It's a tough one, but it's important, and we'd really like to work that.
Okay, I think that's it for our questions. We have a couple minutes until we're going to start the next set, but if JT Weatherman is on, we can turn your camera on and we'll get ready for the next section.
Very good. Thank you, Michelle.
And we'll restart the charts, and we'll be continuing down our journey of flight safety analysis, going into the actual requirements for trajectory analysis. JT, over to you.
Okay, good afternoon all, and thank you, Michelle and Dr. Wild. I'm very pleased to have the opportunity to present the following trajectory analysis sections. To begin, we'll go over some definitions of commonly used terms to get us all on the same page before covering trajectory analysis for normal flight, followed by trajectory analysis for malfunction flight. In reference to launch vehicle performance, trajectory, or stage impact point, nominal means a launch vehicle flight where all vehicle aerodynamic parameters are expected, all vehicle internal and external systems perform exactly as planned, and there are no external perturbing influences other than atmospheric drag and gravity. Normal flight is the flight of a properly performing vehicle whose real-time vacuum instantaneous impact point, or IIP as it is commonly referred, does not deviate from the nominal vacuum instantaneous impact point by more than the sum of the wind effects and the 3 sigma guidance and performance deviations in the uprange, downrange, left or right cross-range directions. Within normal flight, variability and uncertainty exist. Variability describes how the intended trajectory could vary due to conditions known prior to the initiation of flight. One example of variability exists for ISS missions, whereas the launch time into the window elapses, the trajectory must be adjusted to achieve intercept with the ISS. And this topic will be illustrated on the next slide. Uncertainty is how the actual trajectory could differ from the intended trajectory due to random uncertainties and all the parameters which have a significant influence on the vehicle's behavior throughout normal flight. This uncertainty accounts for factors such as motor performance, weather conditions, thrust offsets, and the like. Normal trajectory means a trajectory that describes normal flight. A malfunction trajectory represents a vehicle's deviation capability in the event of a malfunction during flight. This deviation from normal flight is referred to as malfunction flight. Next slide, please. Now, here is an illustration of an example contrasting variability and random uncertainty. This example is representative of an ISS mission originating from Wallops Flight Facility, which would have a defined window in which launch could occur in order to effectively reach the orbit needed to intercept and rendezvous with the ISS. The normal trajectory in the middle of the launch, for the middle of the launch window, is shown as the light blue line. And as launch time into the window elapses, the trajectory must be adjusted to the west to achieve intercept with the ISS. And this yields variability due to conditions known prior to the initiation of flight. The green lines to either side of the nominal represent the uncertainty, which accounts for motor performance, weather conditions, thrust offsets, etc. That could cause the trajectory to differ from the intended trajectory due to random uncertainties in all parameters with a significant influence on the vehicle's behavior throughout normal flight. And these green bounds then would account for the uncertainty for flight beginning at any time in the launch window. Next slide, please. All right, continuing, trajectory analysis for normal flight. Section 117 specifies the constraints and objectives of analyses sufficient to characterize the trajectory of the vehicle during normal flight. Paragraph A states that a flight safety analysis must include trajectory analysis that establishes for all phases of flight as scoped by paragraph A in section 113, the limits of a vehicle's normal flight as defined by the nominal trajectory as well as a set of trajectories sufficient to characterize variability and uncertainty during normal flight. A set of trajectories to characterize variability, which must describe how the trajectory could be expected to vary due to those conditions known prior to flight, and a set of trajectories to characterize uncertainty, which must describe how the trajectory could differ from the intended trajectory due to those random uncertainties and parameters that give a significant influence on a vehicle's behavior throughout normal flight. So this may be a 3 sigma set capturing the left, rightmost, min, max performance scenarios, or a dispersed set of trajectories produced from a large number of Monte Carlo simulations that bounds these conditions. Generally, the FAA considers a significant influence to include any parametric uncertainties within 3 sigma that affect cross-range IIP location or downrange IIP rate by at least 1%, because the IIP location or rate is often a convenient surrogate for the potential impact locations of hazardous debris. And this 1% value is a typical threshold value used in the RCC 321-20 standard and supplement. The rule does not intend for applicants to characterize the influence of all random uncertainties or variability, but only those with a significant influence on the potential impact locations for hazardous debris. Next slide, please. So paragraph B specifies that an analysis must use a 6-degree of freedom trajectory model to satisfy paragraph A of this section. And a 6-degree of freedom, or DOF, 6-DOF model, includes translation in the X, Y, Z directions, as well as the vehicle pitch, yaw, and roll. And this model attempts to more accurately account for aerodynamic forces on a vehicle body. This is in contrast to a simplified trajectory model of lesser fidelity, such as a 3-DOF simulation, which does not accurately account for those aerodynamic forces. Paragraph C specifies that analysis must account for the atmospheric conditions that have an effect on the trajectory. This includes atmospheric profiles that are no less severe than the worst of the conditions under which flight may be attempted. And the analysis must also account for uncertainty in the atmospheric conditions themselves. The FAA recognizes that wind is the primary atmospheric consideration for most vehicles, but for some non-traditional vehicles, other atmospheric parameters such as atmospheric density, humidity, or temperature may affect trajectory and be a part of the flight commit criteria. And the final rule, the rule expressly refers to all atmospheric conditions in paragraph C of section 117. Next slide, please. Now, paragraph D specifies application requirements. This specifies the quantitative input data used to model the vehicle's normal flight in 6 degrees of freedom, which includes comprehensive sets of aerodynamic and mass properties. An applicant must submit the following: a description of the methods used to characterize the vehicle's flight behavior throughout normal flight in accordance with section 115, paragraph C. The quantitative input data, including uncertainties used to model the vehicle's normal flight in 6 degrees of freedom, the worst atmospheric conditions under which flight may be attempted, and a description of how the operator will evaluate the atmospheric conditions and uncertainty in the atmospheric conditions prior to initiating the operation. Representative normal flight trajectory analysis outputs, including the position, velocity, and orientation for each second of flight for the nominal trajectory, a set of trajectories that characterize variability in the intended trajectory based on those conditions known prior to the initiation of flight, and a set of trajectories to characterize how the actual trajectory could differ from the intended trajectory due to random uncertainties. Explanation of details on how to comply with these requirements will be included in Advisory Circular 450.117-1 titled Trajectory Analysis. Next slide, please. Now, a little bit ahead of schedule, we'll address trajectory analysis for malfunction flight. A malfunction trajectory analysis is necessary to determine how far a vehicle can deviate from normal flight. This analysis helps determine potential impact points in the case of a malfunction and is therefore a vital input for the analyses needed to demonstrate compliance with risk criteria. Section 119 specifies the constraints and objectives of analyses sufficient to characterize the possible trajectories of the vehicle during malfunction flight. Beginning with paragraph A, states that a flight safety analysis must include a trajectory analysis that establishes the following: the vehicle's deviation capability in the event of a malfunction during flight, the trajectory dispersion resulting from a reasonably foreseeable malfunction, all reasonably foreseeable malfunctions, and for vehicles using flight abort as a hazard control strategy under Section 108, Part 450, trajectory data or parameters that describe the limits of a useful mission. Important point here is the FAA does not consider the collection of data related to the failure to be a useful mission. Limits of a useful mission will be illustrated on the next slide. An example of means of compliance here for Section 119 will be included in the Trajectory Analysis Advisory Circular. Next slide, please. So we'll pause here as we go through Section 119 to address limits of a useful mission, as this is a relatively new concept. This topic had been briefly addressed by Tom Ricketson earlier in the flight abort section of the workshop. A useful mission means a mission that can attain one or more of its objectives. And as stated on the previous slide, the FAA does not consider the collection of data related to a failure to be a useful mission. Limits of a useful mission means the trajectory data or other parameters that bound the performance of a useful mission, including flight azimuth limits. So shown here is an example of a nominal trajectory in the middle with normal trajectory bounds that account for random uncertainty, as discussed earlier, on either side. The far north and south bounds here represent possible limits of a useful mission. And again, limits of a useful mission are required per Section 119 for those vehicles using flight abort as a hazard control strategy. Every trajectory within the limits of a useful mission that is permitted to fly without abort must meet the collective risk criteria when analyzed as the planned mission per Section 108. Next slide, please. Malfunction trajectory analysis must account for each cause of a malfunction flight, including software and hardware failures. So for each cause of malfunction trajectory, the analysis must characterize the foreseeable trajectories resulting from a malfunction. Paragraph B addresses analysis constraints. A malfunction trajectory analysis must account for each cause of a malfunction flight, including software and hardware failures, for every period of normal flight. The analysis for each type of malfunction must have sufficient temporal and spatial resolution to establish flight safety limits, if any, and individual risk contours that are smooth and continuous. And the analysis must account for the relative probability of occurrence of each malfunction, the probability distribution of position and velocity of the vehicle when each malfunction trajectory will terminate due to vehicle breakup, ground impact, or orbital insertion, along with the cause of termination and the state of the vehicle. The parameters with a significant influence on a trajectory's flight behavior from the time a malfunction begins to cause a flight deviation until the time each malfunction trajectory will terminate due to vehicle breakup, ground impact, or orbital insertion. And finally, the potential for failure of the flight system, if any. So paragraph B2 of Section 119 intentionally excludes termination due to flight abort so that the analyses will produce complete trajectory data, meaning data to be able to account for flight abort action and inaction and risk analyses. Next slide, please. So paragraph C addresses application requirements. An applicant must submit a description of the methodology used to characterize the vehicle's flight behavior throughout malfunction flight in accordance with paragraph C of Section 115, a description of the methodology used to determine the limits of a useful mission in accordance with the same, a description of the input data to characterize the vehicle's malfunction flight behavior, including a list of each cause of malfunction flight considered, a list of each type of malfunction flight for which malfunction flight behavior was characterized, and a quantitative description of the parameters, including uncertainties, with a significant influence on the vehicle's malfunction behavior for each type of malfunction flight characterized. And representative malfunction flight trajectory analysis outputs, including the position and velocity as a function of flight time for each set of trajectories that characterizes a type of malfunction flight, the probability of each set of trajectories that characterizes a type of malfunction flight, and finally, a set of trajectories that characterizes the limits of a useful mission as described in paragraph A3 of this section. So with that, we've gone through the content in the trajectory analysis sections there, and I see that we're a little bit ahead of schedule. Michelle, would
So
we
we
like,
can go ahead and turn this over to Jen Bailey.
very
and we
good,
can continue with debris analysis.
very good. Thank you very much.
Okay, thank you. Okay, so thanks, JT. So 450-121 debris analysis requires applicants to characterize the hazardous debris that can be generated during flight. This includes planned jettison items like payload fairings or boosters, and also unplanned breakups. You can see the definition at the bottom of the slide for hazardous debris. So it's anything that can cause a casualty or loss of functionality of a critical asset. The debris analysis must include all reasonably foreseeable causes of vehicle breakup, which typically includes aerodynamic breakup, explosive breakup, aerothermal breakup, but also intact impacts. The debris analysis should change over time during flight to account for propellant load and any aerodynamic properties of the vehicle and any changes in staging. Okay, next slide. New in Part 450, we're requiring operators to submit a statistically valid debris impact probability distribution. The picture shows it well, what we expect. The model should include these inputs, any forces that can influence the debris impact locations, and all sources of impact dispersion, like atmospheric conditions or winds, the aerodynamic properties of the debris, position and velocity of the vehicle at the start of the breakup, and the uncertainty on the position and velocity, and any imparted velocities due to the breakup. Details about the debris impact probability distribution calculation is included in the high fidelity flight safety analysis advisory circular, which is already on our website. And in the future, it would also be included in the medium fidelity flight safety analysis AC. Okay. Next slide. So paragraph D of 450-121 states the application requirements. An applicant should submit a detailed description of the debris, plus the methodology and all the inputs that went into the debris analysis. Next, Mel will be discussing the population analysis.
Okay, thanks, Jen. Yeah, I'll be talking to the population exposure analysis requirement in Part 450. So Part 450 allows operators to propose impact vulnerability models that are appropriate for the materials used in their operations. As an example, a recent R&D sponsored by the FAA demonstrates that the threshold kinetic energy capable of causing a casualty from a collision with a rigid object is substantially lower than for a collision with an object made of certain composite materials, such as a small UAS. Some of the motivation for conducting population exposure is that spaceflight poses a risk to the public. Debris usually can't be contained to unpopulated areas, and debris can cause injuries. So to quantify risk, locations of people relative to potential debris impacts must be modeled. We say modeled because there's an uncertainty as to where people are and where they are. People are also differentially affected if they are inside a building or outside, so that has to do with the sheltering of people, and there are qualitative models for the vulnerability of people and for the structural response of buildings from debris effects. Next slide, please. Okay, this is so section 123 is the population exposure analysis. Just want to point out that it must also be used to provide input to other public risk analyses to address toxic hazards and far field overpressure blast effects, if there are any. A flight safety analysis must account for the distribution of people for the entire region where there is significant probability of impact of hazardous debris. And the standard of significant means that the scope of the population exposure analysis is bounded by what is necessary to demonstrate compliance with the risk criteria in 450.101A and B. And those are your launch and reentry public safety criteria. And they have to be consistent with the scope of the requirements that were just presented in sections 113 and 115, which are the flight safety analysis requirements and methodology. Some other points are that the exposure analysis must use accurate and timely source data and account for the vulnerability of people to hazardous debris effects. And an explanation and details on how to comply with these requirements will be included in the population exposure advisory circular. Its planned issuance is the third quarter of 2021. And we can go to the next slide, please. Thank you. So section C of the population exposure analysis are the application requirements. So just to reiterate that the analysis must also be used to provide input for other public risk analyses. That is the toxic hazards and far field overpressure blast effects. And also that the FAA specifies that the complete population exposure data must be in tabular form. And it's kind of a depiction here on the lower left of the slide on dispersion areas relative to population centers in a grid form. The top left being population centers that are too large, whereas unless the populations are uniformly distributed, they might not be fully captured within the debris dispersion area. In the upper right, population centers are unnecessarily small, though you'll capture the entire population in the dispersion area. Having such a small grid could take up a lot of computation time. Bottom left kind of shows the grids comparable in size to the dispersion area, and the bottom right shows probably what's more reality, where you have population centers spread out a little more with concentrations in various areas. So that takes me to the end of this section here.
Okay, we're a little ahead of schedule there. Let's see, do we happen to have any questions and answers? Otherwise, we will just take a break and come back for the questions. Our next session is scheduled to start at 2:05 p.m. And then we will cover probability of failure analysis and flight hazard area analysis. And we'll do questions and answers at that time. So please feel free to keep populating questions on anything that you've heard on flight safety analysis. A good chunk of this afternoon is dedicated to flight safety analysis, but we'll see you back at 2:05, give you guys a little bit more of a stretch break and check your email and come back at 2:05. Thanks, everyone. Okay, and welcome back. So we've covered the beginning of our flight safety analysis, and we're going to dive into probability of failure analysis. So like to introduce Ms. Chrissy Zenzi. Please take it away.
Thanks, Michelle. So I'm Chrissy Zenzi, and as Michelle said, I'll be going over 450.131, the probability of failure analysis. So this first chart is really just background information on probability of failure analysis. The purpose of this analysis is to characterize the likelihood of hazard-generating events that could constitute a threat to people or property. There are two approaches to a probability of failure analysis. The first is the top-down approach, where you start with either the overall vehicle probability of failure, or sometimes we see it by stage, and then from there break it down into phases and failure modes. The other approach is the bottom-up approach, where you start with individual component probability of failures and then calculate the overall probability of failure upward. In our Part 450 requirements, we're really encouraging the top-down approach, but in either approach, the overall vehicle probability of failure must be distributed across flight phases and failure modes. So there's just a very simple example shown here. You have an overall vehicle probability of failure of 80%. Break that down into different phases, and then those phases are broken down into different failure modes. Next slide, please. 450.131 codifies performance-based regulations that are consistent with current practices. So we're not asking for anything new in Part 450, but it codifies what we do currently. So in general, for each hazard and phase of flight, a flight safety analysis for a launch or reentry must account for vehicle failure probability, and the probability of failure must be consistent for all hazards and phases of flight. So I'll talk about what that consistent means in the next slide. You'll see for parts 1 and 2, we treat probability of failure differently for the first 2 flights than for subsequent flights. So for a vehicle or stage with fewer than 2 flights, the failure probability estimate must account for the outcome of all previous flights of vehicles developed and launched or re-entered in similar circumstances. So one of those circumstances is manufacturing experience. So historical data shows that manufacturer experience makes a big difference in probability of failure, meaning if you are a new manufacturer making a new vehicle, that generally leads to a higher probability of failure than if you are an experienced manufacturer making a new vehicle or launching a new vehicle. And then if you have a vehicle or stage with 2 or more flights in your history, then the probability of failure must account for the outcome of all previous flights of the vehicle or vehicle stage in a statistically valid manner. And you would need to account for that vehicle or vehicle stage's mishaps or anomalies. Details on how to comply with all of 131 will be included in a future AC, probability of failure AC, which is planned for Q2 2021. Next slide, please. So as I mentioned before, the probability of failure must be consistent for all hazards and phases of flight, meaning the probability of failure has to be consistent, for example, across the debris analysis, the toxics analysis, and the DFO analysis as applicable. That probability of failure should be reasonably conservative. But just to note here, consistent doesn't mean that you can't vary the probability of failure within a given uncertainty for the same event in different contexts. So, for example, you could load the probability of failure within a given uncertainty towards stage 1 for a toxic analysis, but then if there's overflight during stage 2 for the debris analysis, you could load it a little more towards stage 2 in order to be conservative for each case. Okay, next slide, please. So Part B defines failure for probability of failure analysis. So a failure occurs when a vehicle does not complete any phase of normal flight, or when any anomalous condition exhibits the potential for a stage or its debris to impact the Earth or re-enter the atmosphere outside of the normal trajectory envelope during the mission or future mission of similar vehicle capability. And C defines previous flight, which is used in Part A. you have to account for the outcome of previous flights. So for this purpose, previous flight could include flights outside of FAA license activity, such as amateur rocket launches, permitted launches, government launches, foreign launches, etc., or reentries. A previous flight could also include FAA license activity, such as a static fire anomaly, if the outcome of that anomaly exhibits the potential for a stage or its debris to impact the Earth outside of the normal trajectory envelope during a mission or future mission of similar vehicle capability. Next slide, please. So a probability of failure analysis must account for the probability of failure during all phases of flight to ensure public safety, including captive carry, unless the exception in 450.113b applies. I believe we talked about 113b before, but this states that an operator is not required to perform and document a flight safety analysis for a phase or phase of flight, or sorry, for a phase of flight if agreed to by the administrator based on demonstrated reliability. Okay, next slide, please. So Part D discusses allocation of the probability of failure. So Part D was not specified in 431 or 415, 417, but it is consistent with current practices. So a vehicle probability of failure must be distributed across flight phases and failure modes, like I showed in the example at the beginning. The distribution must be consistent with the data available from all previous flights of vehicles developed and launched or re-entered in similar circumstances, and data from previous flights of the subject vehicle itself. This section focuses on the data that must be used and results of the probability of failure analysis, and not necessarily the methodology. Okay, next slide, please. So Part E of 131 discusses the observed versus conditional failure rate. So just to give you a quick definition, the conditional probability of failure assumes the condition that all prior events were successfully completed, whereas the observed probability of failure accounts for the probability of success for the prior event. So I'll show that on the next slide, but before we go there, the regulation itself states that the probability of failure allocation has to account for any significant differences between the observed and the conditional failure rates. The probability of failure analysis must use a constant conditional failure rate for each phase of flight, unless there's clear and convincing evidence otherwise. And then one other note before I move on to the next slide is if either the vehicle or the stage probability of failure is below 10%, there really isn't a big difference between the observed and conditional failure rates. And again, there's going to be a lot more detailed information on this in the AC. Next slide, please. So this shows observed failure rates. So you can see that for higher failure probabilities, you can really see that front-loading effect. And that's because a failure is less likely to occur towards the end of the burn because of the likelihood that a failure occurred earlier in the burn. And you'll see those two lines on the bottom for 10% and 5%. There's really not a big difference over time. So it will look almost the same as the conditional probability of failure for those. But you can really see the effect for the higher probabilities of failure. Okay, next slide, please. Part F goes through the application requirements. So the applicant must submit a description of the methodology used for the probability of failure in accordance with 115C. And Part 2, the applicant must submit a representative set of tabular data and graphs of the predicted failure rate and cumulative failure probability for each foreseeable failure mode. And then there are, on this slide, there are a couple of other papers that are good background material on probability of failure in case anyone's interested. And those are available to the public. Next slide, please. Okay, so that was it for probability of failure analysis. So now I'll be talking about the flight hazard area analysis, which is 450-133. So the flight hazard area analysis section specifies requirements for a flight hazard area analysis, including requirements specific to waterborne vessel hazard areas, land hazard areas, and airspace hazard volumes. An applicant has to identify any regions of land, sea, or air that must be surveyed, publicized, controlled, or evacuated in order to control the risks to the public. Before I get into parts 1 through 6, I'll note the explanation on how to comply with these. There's some information in the high fidelity and medium fidelity flight safety analysis ACs, and there's also an AC specific to airspace and waterborne vessel hazard areas that's planned. Part 1 through 6 of Part A discusses what is needed in a flight hazard area analysis at a minimum. Number 1, the region of land, sea, and air potentially exposed to hazardous debris generated either during normal flight events or all reasonably foreseeable failure modes. Number 2, any hazard controls implemented to control the risks, such as an FTS or wind weighting. Number 3, the limits of a launch or reentry vehicle's normal flight, including worst case atmospheric conditions and any uncertainty in those atmospheric conditions. Number 4, it has to include hazardous debris. 5, sources of debris dispersion in accordance with 121C. And then lastly, it has to include a probability of 1 for any planned debris hazard or planned impact. So the plan, for that last one, we want the applicant to assume a probability of 1 because the planned debris impact should be safe, assuming it occurs. It shouldn't be contingent on failure. So we don't want to do a 50% failure for that or something. We want a probability of 1. And before I go on, there is more background material available in RCC 32120 supplement, which is available to the public. Next slide, please. A couple other notes, hazardous debris, we've discussed that in these slides before, but as a reminder, hazardous debris is any object or substance capable of causing a casualty or loss of functionality to a critical asset. It includes inert and explosive debris, such as an intact vehicle, vehicle fragments, detached vehicle components, payloads, plant genesis bodies, and could include toxic substances. And then sources of debris dispersion, that's just a reference to 121C, which describes FSA requirements for debris propagation. Next slide, please. Okay, so parts B, C, and D discuss the waterborne vessel hazard area requirements, land hazard area, and then part D in a few slides is the aircraft hazard area, otherwise known as airspace hazard volume. So these are all kind of set up the same way. So for B, C, and D, part 1 discusses that it's necessary to contain within 97% probability of containment all debris resulting from normal flight events capable of causing a casualty. So this was discussed, Dr. Weil discussed this earlier, but this is a change from Part 417. Part 417, we used 3 sigma containment, and now we're requiring 97% probability of containment. And this aligns us with practices at the federal ranges, and it allows operators to reduce or otherwise optimize the size of the warning regions. Okay, next slide, please. Okay, so parts 2 for the ship, land, and aircraft discusses which contours are needed for each of those, whether it's probability of impact contours or probability of casualty contours, but the contours needed to meet the risk requirements in 450-101. And as a reminder, people on waterborne vessels are now included in collective and individual risk calculations. However, operators can still use the Part 417 approach and use the 10 to the minus fifth probability of impact contour and keep that clear of ships. Next slide, please. So as I stated before, Part D is for airspace hazard volumes. And one thing I'll note specific to airspace hazard volumes is that the flight hazard area analysis only needs to account for reasonably expected air traffic in a given region. However, we didn't put a specific altitude in here in order to keep it performance-based, and that altitude could be different for different areas of the world. And as I stated before, there is going to be a specific AC for airspace and waterborne vessel hazard areas, and planned issuance is in Q2 of 2021. Next slide, please. Part E describes application requirements. So the applicant will need to submit a description of the methodology, and within that, they'll need to specify the classes of waterborne vessel and aircraft used, as well as the vulnerability criteria employed. And then tabular data and graphs of the results. So one thing to note here is we are requiring 2 sets of contours for the waterborne vessels and aircraft hazard areas. And that's because 2 will demonstrate that the analysis has high enough computational resolution. And also, ATO often needs the 10 to the minus 7 contour for aircraft. Next slide, please. That's it. We're going to Q&A.
Thanks, Chrissy. So we've got a number of questions all queued up. Let's see, who else is going to be joining us? JT, maybe Paul, and Mel. If you guys could turn on your cameras. We're going to be fielding the questions from all of your briefings. So the first question is, what is the intent behind differentiating these 2 trajectory sets? Would a single trajectory set characterize both variability and uncertainty be acceptable?
Thanks, Michelle. So a single set is not acceptable unless it could be determined that there was no significant difference between the 2 sets. One intent is to identify if any conditions that could be identified prior to initiation of the operation, such as liftoff at a certain time into the launch window, would violate the risk criteria so that the launch window cutouts could be identified in the launch commit criteria, for example.
Okay. So are the applications required, the application requirements in 450.119 C2 and 4(3) addressing the limits of a useful mission only applicable to missions that utilize flight abort?
Yes, Michelle, this is a straightforward answer. Yes, the requirements addressing limits of a useful mission is only acceptable to missions that utilize flight abort.
Okay, great. Does the FAA intend to publish guidelines on the format and reference frames in which operators should provide this data?
Good to go, Michelle. I'll answer that one as well. So yes, trajectory analysis advisory circular is planned with the preferred format and preferred reference frames included. The FAA anticipates that using the preferred format and reference frames will improve the efficiency of the FAA evaluation. However, an operator could choose to use other formats and reference frames if they like.
Okay, great. Also, parameters with a significant influence on the vehicle's flight behavior needs clarification. Are these essentially the normal values an applicant includes in 80-12?
Michelle, to answer this one, provide the clarification, I'll look to the preamble to the final rule, which states, generally, the FAA considers a significant influence to include any parametric uncertainties within 3 sigma that affect the cross-range IIP location or downrange IIP rate by at least 1%, because the IIP location and rate is often a convenient surrogate for the potential impact locations of hazardous debris. So that's the definition that the operator should refer to.
Okay. How many trajectories are expected to be needed to characterize a type of malfunction, JT?
Well, Michelle, there is no specific number, but the performance standard is given in paragraph B of section 119, which states The analysis for each type of malfunction must have sufficient temporal and spatial resolution to establish flight safety limits, if any, and include and individual risk contours that are smooth and continuous. So that's ultimately what you'll be looking to achieve.
Okay. Is a single breakup analysis of the worst case cause of vehicle breakup acceptable?
Let's see.
So I'll go ahead and take that one since we don't have Jen on the line. So conceivably, yes, but it's often very difficult to foresee what is truly a conservative single set. It depends on many things, the sizes of the dispersions, the nature of the public exposure, whether they're sheltered or not. So, you know, the example of the Columbia debris, you know, they had a lot of small debris. You know, would an operator have thought that that was conservative? I've got so many fragments, but you know, because they were effectively sheltered from those fragments, the answer is no. So, in general, no.
Okay. Does the FAA consider a significant probability, or what does the FAA consider a significant probability with respect to the probability analysis in 450-124?
So I think this was a question with respect to the population, since we use that term, a significant probability. You have to account for those population centers. Mel, if you wanted to take that one, go ahead. If not, I can handle it.
Yeah, I could take that. That's stated in the preamble. The standard of significant, that means the scope of the population exposure analysis. It's bounded by what's necessary to demonstrate compliance with the risk criterion 450-101, and also consistent with the scope of the requirements in 450-113 and 115, which are the flight analysis requirements and methodology.
Okay. Is it correct to assume that this requirement is limited to vehicle anomalies that occur during flight?
So Chrissy, I think they're asking about the probability of failure section, so you can go ahead and take that one.
Sure. So it could, it could occur, the probability of failure could include events that occurred outside of launch, such as a static fire, if that failure exhibited the potential for a stage to fail during flight.
So an example of that would have been the Amos 6 event, where that explosion occurred on the pad during static fire. But after investigating the root cause, it was found that that could have occurred during flight. So we counted it.
Okay. Can the FAA clarify the meaning of this provision, quote, or any future mission of similar vehicle capability?
Chrissy, did you want to take that one, or do you want me to?
Yeah, can you take that one?
Okay. So I'm looking at the question, clarify the meaning of the provision or any future mission of a similar vehicle capability. Yes, so that might be, for example, you have a vehicle, I remember the Titan, it could, of course, go to geotransfer orbit. So you'd be launching, you know, at low inclination from the eastern range, for example. And a failure that occurred later in flight, even post-orbital insertion on a mission like that, could occur prior to orbital insertion if you're flying to a different inclination, especially a high inclination. Similar launch from Vandenberg, for example, that type of failure would have been expected to occur prior to orbital insertion. So inclination is one example. different inclinations.
Okay. For 450-131A1, does the requirement still apply if there's no way to get data about certain similar circumstance vehicles? For instance, if the former operator of the vehicle has since gone out of business or refuses to release or publish its data?
I can take this one. So I think it would be it'd be limited to what's publicly available. And also I'll note that the AC will have some guidance on allocations. But yeah, to answer the question, it's what's publicly available.
Now, if I could just add on, since all we're really looking at is the flight history and, was the flight a success or a failure, that type of information is generally publicly available.
Okay. Another probability failure analysis question. It requires all similar vehicles to be analyzed. Is that all similar vehicles by a specific launcher or manufacturer, or does it mean all similar vehicles by anyone?
If I understand the question right, it's the second one. So it's all vehicles, again, publicly available data.
Yeah, I would just add on, it's not necessarily a similar vehicle, but it's vehicles developed and launched under similar circumstances. So the, that is a broader category. Now, the design of the vehicle, okay, of course, is important, but, there's more to it than just that.
Okay, great. Would a flight outside of the US be considered a previous flight?
Yes, so it could. But again, we know that data is not always as available. So we would understand that. But yeah.
So it sounds like it's really going to all similar vehicles when we have the data available publicly.
Correct.
Okay. Does the population exposure analysis have to account for transient populations, specifically those who spend much of their life on boats at sea? There's a subpart to this. Or for cases where the only potential for debris is in the broad ocean, can population exposure analyses be omitted or summarized as something like the only potential for hazard is to broad open ocean areas with no population?
Mel, if you want to take that one, go ahead. Otherwise, I can answer.
I can probably get some of that, but why don't you go ahead and take all of it?
Okay, no problem. So, as noted in the section on 101, risk management is open now to people on waterborne vessels, so they can be included in the expected casualty analysis. Now, the old way of doing business is still an option. You can define your hazard areas based on the 1 × 10⁻⁵ probability of impact. And then if there are no vessels within that hazard area, no need to consider the density of ships, for example, outside of that hazard area. So if there was only regions of the ocean that are subject to hazardous debris impacts, that can be, there is data available on the density of different types of ships in different areas. In fact, there's a DOT website that provides a great deal of information on that. But whether you scored it inside the population exposure analysis for 124 or under some other part of the analysis, it's not that important. We just want to make sure that those risks are accounted for.
Okay. 3 sigma containment would imply a 0.9987 probability, or simply 0.99. So is the 97% a typo? Would 0.97 correspond to just over 2 sigma in normal distribution?
So what the slide said is that in 417, we used 3 sigma, and part 450, we're updating to the 97% probability of containment. So it is a little less stringent, and it aligns us with the federal ranges. That's why we updated.
97% is definitely not a typo.
Okay. If we include notice to airmen and mariners, are we allowed to assume that all aircraft and watercraft will obey those notices, thus allowing for no craft to be within a keep-out zone we specify for launch?
Paul, feel free to add on to this, but I think this is going to be discussed in the control of hazard areas section. I'm not sure when that's scheduled for, tomorrow maybe.
Yeah. So in general, the answer is no. That's a very sweeping assumption to assume that everybody would obey. But in terms of the need for surveillance, surveillance is only mandatory to ensure that there's no one exposed to greater than 1 times 10 to the minus 6 probability of casualty. So that's generally a very small subset of the total ship hazard area.
Okay. Any other questions coming in? Please get them in now so that we don't have anything else in our queue at the moment. Our next session is due to start on debris risk analysis at 2:50. We'll give another minute or so for questions to come in, and otherwise we will break until 2:50. So we'll just give it another minute or so. Is there any other points that the speakers wanted to make on their topics?
I'd just like to take the opportunity to lavish some praise on our flight safety analysis team. Very proud of this team. Thank you, guys.
Yeah, this was a big part of the transition from NPRM to final rule, and the flight safety analysis got much more tightened up and performance-based. So good job, guys. Okay, I think we're going to go ahead and break until 2:50. And we will see everyone back. Okay, we want to bring some folks back. We're going to begin here shortly. Our next session is on debris risk analysis with JT Weatherman. So without further ado, JT, go ahead and start your presentation.
Thank you, Michelle. Thank you. So yes, now we'll cover section 135 pertaining to debris risk analysis. To begin, paragraph A states that a flight safety analysis must include a debris risk analysis that demonstrates compliance with safety criteria specified in section 101, either prior to the day of the operation, while accounting for all foreseeable conditions within the flight commit criteria, or during the countdown using the best available input data, including flight commit criteria and flight abort rules. Any valid debris risk analysis must account for flight commit criteria and flight abort rules if such controls are necessary to ensure compliance with the criteria in section 101. Since the debris risk analysis is typically used to identify flight commit criteria and flight abort rules, such as wind constraints, this analysis may be iterative. And likewise, the flight rules would also be evaluated using the debris risk analysis and possibly modified as necessary in an iterative fashion. An example of means of compliance for section 135 can be found in the High Fidelity Flight Safety Analysis Advisory Circular. Next slide, please. Paragraph B addresses casualty area and consequence analysis. It states that a debris risk analysis must model the casualty area and compute the predicted consequences of each reasonably foreseeable failure mode in any significant period of flight in terms of conditional expected casualties. It further states what the casualty area and consequence analysis must account for, which is, first, All relevant debris fragment characteristics and the characteristics of a representative person exposed to any potential debris hazard. Debris fragment characteristics include their size, shape, weight, beta value, imparted velocities, number of each type of fragment. Characteristics of a representative person exposed to any potential debris hazard here refers to the assumed dimensions of a person used in the modeling. Next, statistically valid debris impact probability distributions. And a side note here, per section 121, paragraph C, the debris analysis must compute statistically valid debris impact probability distributions of all hazardous debris, which are key inputs here. These are driven significantly by trajectory dispersion, as we mentioned in the trajectory analysis section earlier. Also, any impact or effects of hazardous debris. This is a performance-based requirement. If a hazard is presented, a user must account for these. Hazardous debris includes all hazard sources, such as the potential for any toxic or explosive energy releases. This is further described as any object or substance capable of causing a casualty or loss of functionality to a critical asset. And hazardous debris includes inert debris and explosive debris, such that an intact vehicle, vehicle fragments, any detached vehicle component, whether intact or in fragments, a vehicle's payload, and any planned jettison bodies. So this could be interpreted to include direct or indirect impacts. And finally, the vulnerability of people to debris impact or effects, including effects of buildings, ground vehicles, waterborne vessel, and aircraft upon the vulnerability of any occupants to these. This captures how vulnerable a structure or vehicle is and to what degree occupants are hazarded. Effects of atmospheric conditions on debris impact and effects. And here we're talking how debris will be expected to propagate. Impact speed and angle, accounting for motion of impacted vehicles, which we'll again mention in the following slide. Uncertainty in input data, such as fragment impact parameters, and uncertainty in the modeling methodology itself. Next slide, please. Since paragraph B mentions the topic of reasonably foreseeable failure modes, I thought it would be good to briefly go over some of them typically considered in an analysis. First, on-trajectory explosion is pretty self-explanatory here. The failure may result from an explosive overpressure or structural or other failure leading to propellant mixing and subsequent explosion at any point given in a given flight. Low thrust or loss of thrust may result from one or more engine failures on a launch vehicle, resulting in insufficient thrust to achieve its intended trajectory. A malfunction turn characterization, and in this scenario, the vehicle understands where it's trying to go, but it cannot get there. A malfunction turn is representative of a hardware issue, possibly a TVC hardware failure resulting from a condition where the vehicle experiences a thrust vector that is offset from the planned vector alignment with the vehicle body, causing the vehicle to enter a turn that deviates from the normal trajectory. And in contrast to malfunction turn, random attitude failures are representative of a guidance, navigation, and control system failure, leading the vehicle to assume an alternate trajectory in a controlled fashion, trimming out and ultimately flying the new heading to the end of powered flight, breakup, or ground impact. This type of failure is of greater concern as the failure would more likely be survivable, potentially allowing the IIP of the vehicle to deviate further from the intended trajectory without breakup. The next two failure characterizations are considered subset cases of random attitude, as they are specific resulting possibilities of a type of GNC system failure. The first, the GNC system components may have been improperly programmed or calibrated, resulting in an incorrect azimuth failure beginning at T0, where a vehicle may attempt to fly the intended nominal trajectory oriented down an incorrect flight azimuth. Another failure characterization for ground launch vehicles occurs when the normal trajectory flight fails to execute the pitch over maneuver and begin turning the vehicle into the downrange direction, resulting in a straight up failure. In addition to these, there may be other relevant failures to consider specific to each launch vehicle. Next slide, please. So here are some examples of important vulnerability factors. First, I'll mention that safety models range from applying threshold values to a probabilistic approach. For example, a fragment with a kinetic energy above a certain threshold will always deliver damage, while a probabilistic method may assume that there would be a probability of the fragment delivering that damage. So vulnerability factors for structures here. Roof construction type drives a structure's vulnerability to inert impacts. Certain construction methods are understood to be more robust. Here at left is a graphic describing considerations for a safety model for structures, specifying different characterization of roof failure modes, including puncture, membrane flexure, beam failure, column failure, and each of these may be assigned a separate consequence. Similarly, wall and window construction drive a structure's vulnerability to explosive debris impacts. And vulnerability factors for aircraft here, characteristics of an aircraft.
Can the production line still hear and see me?
Yes, I can hear you, Michelle.
Okay, we must have lost JT. Just if folks could stand by for a minute, we'll give JT a minute to catch up. Otherwise, Paul, you are on standby to be JT's backup in the case of technical problems. Paul, are you able to join us?
Yes, I'm available to join.
Okay, JT is on
Let me
chart.
get off the Q&A line.
Okay, thanks. JT is on chart 83.
Okay. I certainly hope JT can join at some point, but I'll pinch hit for him.
Thank you.
So yeah, this slide basically just shows different aspects of the vulnerability analysis. And a question has come up about, the importance of the aircraft speed, and indeed the speed of the aircraft, very important parameter. So of course it needs to be accounted for. Okay, next slide, please. Okay, so here we have a slide about the application requirements. So one of the most important parts that we've tried to drive home is that the risks need to be demonstrated to be acceptable, at the time that the operation is initiated, and therefore the application needs to include a description of how the operator will account for the conditions immediately prior to enabling the flight of a launch vehicle or reentry of a reentry vehicle. So that often involves the weather conditions. It doesn't mean that you have to have a real-time risk analysis, but just that you verify that the conditions, the prevailing conditions, are consistent with the flight commit criteria that ensures compliance with the risk criteria. Okay, so the conditions immediately prior, of course, include what the final trajectory would be. So for example, we pointed out if you're doing a rendezvous mission that's going orbital, the later you get in the window, the farther your nominal trajectory will progress to the west. And so, of course, you have to ensure that at the time that you fly, the risks are acceptable based on that final trajectory, as well as other things, the exposure of people. This gets into, if there's been a fouler in a hazard area, if a person is a greater than 10 to the minus 6 probability of casualty, that would necessitate a hold for the launch, etc. So item number 4 talks about the effective casualty area. The effective casualty area is an aggregate casualty area of each piece of debris created by the vehicle at a particular point in the trajectory. So if you think about an explosive impact, in reality, of course, the probability of a casualty depends on the distance away from the explosion. But the effective casualty area we have as a modeling construct. And so the effective casualty area is mathematically equivalent to the real casualty area, but with the assumption that if you're in this affected casualty area, it's 100% probability of casualty. So I see that JT is back, and I do not want to steal his thunder. So JT, if you're on.
And let's do a sound check with you.
Thank you, Dr. Wild. I appreciate you filling in there while I had that momentary dropout. I'm sorry for the interruption.
No trouble.
No worries. Go back to you, JT.
Thank you very much. So here we are. We are on, let's see, part C. Is that correct?
Yeah, I finished up this one.
Oh, finished up this one. Okay, so we're on to the next. Very good. So continuing with paragraph C, which addresses application requirements. An applicant must submit a description of the methods used to demonstrate compliance with the safety criteria contained in section 101 in accordance with section 115, paragraph C, which addresses application requirements applied to flight safety analysis methods, including a description of how the operator will account for the conditions immediately prior to enabling the flight of a launch vehicle or the reentry of a reentry vehicle, such that the final trajectory, atmospheric conditions, and the exposure of people. So again, in paragraph C1, it requires an operator to describe how they will account for the conditions immediately prior to enabling the operation, including the final trajectory, atmospheric conditions, and the anticipated exposure of people. And this is, of course, because the risk criteria must be met given the conditions at the time of the operation is initiated per section 101, paragraphs A and B. Additionally, an applicant must submit a description of the atmospheric data used as an input to the debris risk analysis, the effective unsheltered casualty area for all fragment classes, assuming a representative impact vector, and the effective casualty area for all fragment classes for a representative type of building, ground vehicle, waterborne vessel, and aircraft, assuming a representative impact vector. So according to section 7 of 401, effective casualty area means the aggregate casualty area of each piece of debris created by a vehicle failure at a particular point on its trajectory. And here it's noted that in reality, the probability of casualty decreases with the distance from an explosive impact, and the effective casualty area is a modeling construct, the area within which 100% of the population are assumed to be a casualty, and outside of which 100% of the population are assumed to be unhurt. Next slide, please. Let's see here. Good to go. All right. So let's see. I would like to continue through paragraph C5. I'm afraid that I may have mispicked where we were just there. I was going to continue on the previous slide, please. Through application requirements. Let's see. An applicant must further submit collective and individual risk analyses outputs under representative conditions and the worst foreseeable conditions, including total collective casualty expectation for the proposed operation, considering all reasonably foreseeable failure modes and scenarios, a list of the collective risk contribution for at least the top 10 population centers and all centers with collective risk exceeding 1% of the collective risk criteria in section 101, paragraph A1 or B1, and a list of the maximum individual probability of casualty for the top 10 population centers and all centers that exceed 10% of individual risk criteria in section 101, paragraph A2 or B2, and a list of conditional collective casualty expectation for each failure mode for each significant period of flight under representative conditions and the worst foreseeable conditions. And here, worst foreseeable condition means those conditions that produce the highest individual, collective, and conditional risks under which the operator would initiate the operation. And with that, this concludes the debris risk analysis section of the workshop. And I'll now hand it back over to Dr. Paul Wild to address far field overpressure blast effects analysis.
Thanks, JT. I think we're pretty much right on time. So before we get into the specific requirements for the far field overpressure risk analysis, this slide provides an overview of this subject. So starting at the upper right, you see a cartoon that shows a potential accident scenario that could involve a large explosion. any intact impact of the vehicle is a potential threat to cause an extremely large explosion. I mentioned previously, Space Shuttle was an example of a vehicle that could create an explosion that's 100 times, at least 100 times larger than the explosion that destroyed the Murrah building in Oklahoma City and killed over 168 people. 168 people lost, tragically. So as part of the debris risk analysis that JT was just talking about, it's often possible or necessary to construct a yield histogram. So the yield histogram is the probability of various sizes of explosions. And so for a given yield at a given probability level, once you have that, then you proceed to the next box where we look at how the blast wave would be propagated through the atmosphere. And that's very sensitive to the weather conditions when we're talking about these low overpressures. So far field basically means instant overpressures that are below 1 psi. And there's a technique called ray tracing, which was originally invented by Lord Kelvin. And you can trace the rays through the atmosphere, accounting for the sonic velocity profile, which is affected by the temperature at various altitudes, as well as the wind speed and direction at various altitudes. And so under specific weather conditions, it's possible to get what we call a focus. And so you see those two rays there initially getting bent up to higher levels in the atmosphere and then coming back down and converging. And at that convergence point, that you could potentially have a focusing condition and a much elevated peak overpressure compared to standard isothermal conditions. In fact, you can get broken windows in that location, whereas if you were below the apex of those rays, you might not even hear this explosion. Such an event happened in San Antonio, Texas in the early 1960s. It's kind of the quintessential event for this phenomena called the Medina event, where a munitions depot exploded. 110,000 pounds approximately was the equivalent TNT yield, and that resulted in over 3,000 windows reported broken in downtown San Antonio, whereas there were areas in between the explosion site and where those windows were broken, where there was in fact no damage. So, so there's pretty sophisticated algorithms to basically keep track of where these overpressures might be concentrated, so that once you get to a given location, you can predict the peak overpressure. That can be modified by the presence of the building. So you have the reflected overpressure that the windows actually experience. Then the model would look at the dynamic response of the window. It's basically a single degree of freedom oscillator, flat plate, and it's possible then to compute the peak deflection and the peak stresses. And when you compare those to the dynamic capacity of the window, you can estimate the probability of breakage. If you do have breakage, then basically the imbalance of overpressure on the outside compared to the inside of the building accelerates those window shards, glass shards into the room. In some cases, they can fall out of the room. And if they fall from upper floors, they can be also very hazardous. So the model would typically then track those potential fragments and account for if you have people at those locations. They could be standing, they could be sitting, they could be laying down. A region of casualties behind different windows, and different windows behave very differently. If you have large, especially single pane annealed glass windows, they're much more susceptible to breakage compared to small windows or tempered glass windows or dual pane windows. So after that, when you have this potential region of casualties, you can synthesize that over all the structures that are exposed and all the population areas, and eventually get the expected casualties. And then typically we have contours that show predicted overpressure and probability of focusing in different regions. So there's a lot of technical information that was published on this in section 5.3 of a book called Safety Design for Space Operations, published by Elsevier. Next slide, please. So now we have the actual requirements of 450-137. Starting in paragraph A, we'll see that the regulation allows two different means or methods to demonstrate compliance. One is basically a screening analysis that's conducted prior to the day of the operation, accounting for all the foreseeable conditions within the flight commit criteria. And there's an ANSI standard S as in Sam 2.20-1983. That was also referenced in Appendix A to 417. It provides a relatively easy means to establish that no further analysis is necessary based on the maximum yield that's predicted for a particular operation and the distance to nearby populations. So specifically in that ANSI standard, if you look at figure 26, it shows a plot of the so-called no damage yield limits as a function of the distance to population centers of various sizes. And basically, if the size of the explosion from the potential explosion from the launch vehicle operation is below the no damage yield limit specified in that figure, then 450-137A1 would be satisfied without any further analysis. So there's a little off ramp there. That has been done by past operators, but it's sometimes necessary to move on to Alpha 2 and perform an analysis during the countdown using the best available input data. So as I mentioned, the meteorological conditions have an extreme influence on these risks. Very, very sensitive to the wind conditions, the potential inversions. So measurement of the wind conditions and those atmospheric conditions is an extremely important part of any far field overpressure blast effects analysis. We will have an example means of compliance in an AC that's slated to come out in the third quarter of 2021. Paragraph B goes into the analysis constraints about what must be accounted for. It's basically a laundry list of the types of things that I talked about on the first slide. Next slide, please. Okay, so this slide shows the application requirements for section 450-137. We did streamline these a fair amount relative to what was in the NPRM, but it's still a fairly extensive set of application requirements. And so you see these things, I'm not gonna read them off to you, but of course they cover the types of things that we talked about on the first slide. I wanted to emphasize item number 8 there, a description of the meteorological measurements used as input. These days, you can get some terrific weather information from various sources. Of course, the National Weather Service, the Air Force provides some terrific forecasted weather products. So it's not necessary that you as an operator would have to perform your own measurements. Although the wind conditions at the launch site at low altitudes is extremely important, and it's not untypical to have a tower, an instrumented tower with some wind conditions and temperature measurements there. So thank you for your attention. Now it's over to Mel for 451.39.
Thank you, Dr. Wild. So I'll be just going over the toxic hazards for flight requirements in 450, section 139. In the final rule, the FAA clarifies that operators are not required to perform a toxic release hazard analysis for kerosene-based fuels unless directed by the administrator. Otherwise, this section applies to any launch or reentry vehicle, including all vehicle components and payloads that use toxic propellants or other toxic chemicals. And an example of a means of compliance for this section can be found in the advisory circular that's planned to be issued in the third quarter of 2021. Next slide, please. Okay, paragraph B requires an operator to conduct a toxic release hazard analysis and manage the risk of casualties from exposure to toxic release, either through containing the hazards, which will be discussed in section D, or by performing a toxic risk assessment in paragraph E, and that they protect the public consistent with the safety criteria in 450.101. Okay, the toxic, that kind of discusses sections 1 and 2. Actually, section 1 of B is to conduct a toxic release hazard analysis in accordance with paragraph C. So that will be coming up as well. Item 3 is to establish a flight commit criteria based on the results of its toxic release hazard analysis and either toxic containment or risk assessment for any necessary evacuation of the public from any toxic hazard area. And a toxic hazard area is defined as a region on the Earth's surface where the toxic concentrations and durations may be greater than accepted toxic thresholds for acute casualty in the event of a worst case or maximum credible release scenario during launch or reentry. Next slide, please. This is kind of an overview of the toxic risk analysis. I'll kind of step through it and try to keep on time here. So for flight, toxic hazards begin essentially at the ignition, where you'll have a nominal launch or an accident, and the meteorological conditions will be an input to that. So in either case, formation of a toxic cloud occurs, it becomes dispersed, and it will concentrate over time at various receptors downwind. There are exposure response functions that address the susceptibility of subpopulations and those severity levels for various toxic commodities. So these will get input to the distribution of number of casualties for a given probability of an event for each receptor, each population group, and severity level. These will employ either some sort of distribution, binomial, approximate binormal, or Poisson distribution. And this distribution will be generated over all the receptors for each scenario, looking at each population group and their severity level and overall. So then we'll aggregate that over the scenarios to obtain a distribution of the number of casualties for the mission. And again, looking at each population group, severity level, and overall to get the end product, the risk end product being the risk profile at the bottom right, as you see there. The total risk in this case will be the the area under the curve. So next slide, please. Getting back to the regulation text, section C sets forth the requirements for the toxic release hazard analysis, and it should account for any toxic release that could occur during nominal or non-nominal flight. It should include a worst case release scenario analysis or a maximum credible release scenario process analysis for each process. I should determine if a toxic release can occur based on evaluation of the chemical compositions and quantities, and for other chemicals, vehicle materials, combustion products, and other possible toxic release scenarios. Should account for both normal combustion products and any unreacted propellants, phase change or chemical derivatives of released substances, and account for any operational constraints and emergency procedures that provide protection from toxic release. Picture on the left there is an anomaly from the 80s of the Titan 34D at Vandenberg. Kind of gives you a look at the how immense a toxic release can be. Next slide. Okay, paragraph D talks about the toxic containment for toxic hazards. It requires an operator to manage the risk of casualty from exposure, either by evacuating or being prepared to evacuate the public from a toxic hazard area, or by employing meteorological constraints. In either scenario, the operator would be required to ensure that the public will not be within a toxic hazard area in the event of a worst case or maximum credible release scenario. Next slide, please. Okay, this is the or, the either or. So containment is one method. Paragraph E talks about toxic risk assessment. And this must account for the airborne concentration and duration thresholds of toxic propellants or other chemicals, the physical phenomena expected to influence any toxic concentration and duration. So there's not, that's kind of the gist of what this all says here. I won't read through the whole slide. Next slide, please. Okay, for the application requirements, the means of compliance at the bottom there, I should point out, is for the previous page, but for paragraph E1, the means of compliance are the acute exposure guideline level 2, emergency response planning guidelines level 2, or the short-term public emergency guidance level. For the application requirements, this is a list of the items that are required. Discussed most of those already. It pretty much addresses what was discussed in the previous section. It's kind of a laundry list right there. We can go to the next slide. And finally, the last section here, item 8, toxin containment. Again, as discussed earlier, to identify evacuation plans or meteorological constraints. Make sure it addresses the risk criteria in 450-101, and a description of the population exposure input data should be used in accordance with 450.123. And I believe that covers this section.
Okay, so I think we need to have back for our Q&A session the speakers for Chrissy, JT, Paul Wild, Mel, some others. Okay, so Our first question for Paul is, are conditional expected casualty results required even when CEC is not used to meet any other requirements? CEC analysis has a higher barrier of entry than standard debris analysis due to the sampling rates required to achieve smooth conditional results.
Right. Thanks, Michelle. So the short answer is no. If the FAA approved an operator's license application without consideration of CEC results, so for example, if you chose to have a flight safety system that complied with 450.145, and then you met the requirements in 450.108C6, then the application requirement in 135, which is 135C5(4), would not be applicable.
Okay. Will the FAA be providing models and references on population susceptibility to injury related to shelter types, window types, time of day, to lower the barrier of entry to meeting these requirements?
So I think this question was with respect to 450.137 for the far field overpressure risk analysis. So we will be providing a means of compliance for 137. There are some vulnerability models available. So for example, in RCC 321-20, they're called pressure impulse diagrams for, the most susceptible types of window types. And they give the probability of casualty in typical structure types.
Okay. So JT, this question is for you. Will the FAA be providing the models and reference data associated with human vulnerability in buildings and vehicle sheltering effects to, again, lower that barrier of entry to meeting these requirements? Or are the operators expected to develop their own models?
All right, Michelle, to answer this one, RCC 321-20 supplement provides numerous thresholds to account for the vulnerability of people in various shelter types, and operators can use the vulnerability models in that reference, RCC 321-20 supplement.
Okay. Is this specifically for aircraft, or does the FAA expect the motion of automobiles and vessels to be modeled as well?
Well, this would apply to aircraft in general, because aircraft, the velocity of the receptor, it significantly influences the vulnerability of the occupants. So in general, the operator should assess if the velocity of other vehicles would significantly influence the vulnerability of the occupants to their hazardous debris.
Okay. Are these results required for both pre-flight analysis and final forecast during the countdown?
Yes, the representative results are required with the license application. In cases, the operational risks used to demonstrate compliance with Section 101 of Part 450 would be subject to inspection by FAA safety inspectors.
Okay. And what is the purpose of providing results for both representative conditions and the worst foreseeable conditions?
Well, as stated in the preamble to the final rule, an operator can submit the same debris risk analysis results for the representative conditions and the worst foreseeable conditions in cases where there is no difference between representative conditions and the worst foreseeable conditions that are significant to public safety. However, the FAA foresees the potential for situations where the differences between the representative conditions and the worst foreseeable conditions would require additional operational mitigations. An example of this would be running the debris risk analysis using input data for the atmospheric conditions that lead to risk just below the limits set in Section 101, that is the worst foreseeable conditions, and running the debris risk analysis using more typical atmospheric conditions that produces risk clearly below the limits.
Okay, I think that's all the questions we have queued up. If you have any other questions on the flight safety analysis, please type them in and we'll get them queued up. Otherwise, that really concludes our session on flight safety analysis. Our next session coming up is on computing systems, and we'll be taking a break before that while we wait to see if there's any additional questions coming in. Okay, we don't see any questions coming in, so we're going to go ahead and break until 3:50. And at that point, we will come up on our last session of the day on computing systems. Thanks, everyone. Okay, I want to welcome folks back. We are about to start our last session of day 2. If I could have Jay turn on his camera. And perhaps, maybe not the virtual background. Is it working okay? There we go, that looks much better. Perfect, okay. So we are going to go into, I think in the overview I talked about there's some prescribed hazard controls, and some of them are for safety critical hardware and computing systems. So our next 3 sessions are going to be on those. And the first one to round off the day today is on computing systems. And I'd like to welcome Mr. Jay Nafis.
Thanks, Michelle. So this next slide is you could think of this as the requirements that we use to design 450-141, the Computing Systems and Software Regulation. You've heard reference to it a number of times in the preceding presentations. And we retained this separate section because much like mental health is a separate discipline within all of medicine, software safety or computing system safety is a separate section of the regulation because it's a concentration of complexity with unique behaviors and behavior potentials and risk potentials that merit separate consideration. So these are the requirements that we use to design the requirements in 450-141. It needs to produce an understanding of computing systems and how to make them safe. It needs to fit with a wide range of development processes and be as technology independent as we can. And it also needs to work constructively with system safety, precisely because, as Christopher and others mentioned, it's a unique component within system safety that handles those unique concentrations of complexity. Next slide. To understand the regulation, here's a few definitions that are key to untangling it. A computing system safety item is a term you'll hear often. It's any software or data that implements a capability that can present a hazard to the public by its intended operation, unintended operation, or non-operation. A computing system safety item will often contain several software functions assembled to meet a group of related requirements, such as an autonomous flight safety system or a GPS receiver. Degree of control is another key concept here. Computing system safety items' importance in the causal chain for a hazard is its degree of control. That's either in causing or preventing a hazard. Now, this can be analogous to degree of autonomy, which appears in some software standards. There are a number of ways of assessing degree of control. The key part of it is that it's a measure of the importance of a computing system safety item in a hazard's causal chains. Level of criticality is related to that. And level of criticality is the combination of a computing system safety item's importance in the causal chain for a given hazard, its degree of control, and the severity of that hazard. It's similar to risk's definition of severity and likelihood, where instead we use severity and degree of control. Another term that could be confusing is safety requirement. In the context of this of 450-141, a safety requirement is a computing system requirement or software requirement defined for a computing system safety item that specifies an attribute or function that presents, prevents, or is otherwise involved in a hazard to the public. So these are the subset of your computing system or software design requirements that specify safety functionality. Those are the safety requirements that we're referring to in the discussion of 141. Next slide. So you've noticed from prior presentations that computing system safety effectively executes as a subroutine of system safety. 450-141 is applicable whenever a software or computing system is found to present or prevent a hazard to the public. This subroutine then derives appropriate risk controls for those computing systems and then produces outputs that can be incorporated back into the main system safety analyses. The rule is structured to answer 4 key questions. What's important for safety and how important is it, with the identification of computing system safety items and assessment of their level of criticality, degree of control in Part A. Then it also answers what does each item need to do to be safe. Part 141B requires identification, verification, and validation of the safety requirements for computing system safety items. 141C answers what processes introduce or limit risks. This defines the expectations for development processes that will control the risk of the computing system safety items that are developed by them. And 141D answers what do you need to submit for a license. Next slide. In our advisory circular associated with this regulation, we specify 2 means of compliance. One is to tailor RCC 319-19 or later, which is recommended for licenses where a flight safety system contains all of the computing system safety items, or for operations at federal ranges that require RCC tailoring besides. And the tailored version must be submitted during pre-application consultation, included in the application. The second path is direct compliance with the 4 subparts of 141. Safety element approvals under 141 can be sought for either a computing system safety item as a whole, such as an AFSS, which I've found a good example because it tends to be standalone, or for computing system safety processes, either the safety requirement identification and verification validation processes under 141B, or for the main software development processes under 141C. Next slide. Here are the detailed requirements. You can read them on the right. The big picture of 141A is that it scales level of rigor in software development based on each computing system safety item's level of criticality. It facilitates streamlining of the other parts of 141 by identifying those computing system safety items that have importance for public safety. Next slide. Now, a computing system safety item is a fairly broad term. It includes software or computing systems that could interfere with the operation of a computing system safety item, as well as each computing system safety item's human and hardware interfaces. Each identified computing system safety item should be made evident in one or more standalone documents, or FHA or other system safety products. The applicant and the FAA should work to agree on those on the list of computing system safety items during pre-application consultation. Next slide. Now, 141A requires criticality assessments, level criticality for each computing system safety item according to the hazard severity and degree of control for the hazards associated with it. In the advisory circular, we lay out two potential methods for identifying the severity or consequence, which are the public safety consequence categories adapted from MIL Standard 882E, or the functional hazard analysis consequence categories that would be defined in analyses from 450, 107, and 109. For degree of control, there's more opportunity for innovation. We lay out 5 different methods for assessing degree of control. 1, the conservative assumption, assume all computing system safety items have the highest degree of control. 2, use the software control categories from, or software categories from RCC 319-19. This would be for those operations where a flight safety system contains all of the computing system safety items, but is not tailoring 319 otherwise. Method 3, you could use the MIL Standard 882E software control categories. And very similar to that, method 4, NASA guidebooks have software control categories defined as well. And a 5th method we've laid out is to use fault tolerance as the criterion for degree of control. Next slide. 141B sets out requirements for safety requirements. It requires the identification and evaluation of safety requirements for each computing system safety item. It then requires to ensure that the safety requirements are complete and correct, implement them as you would for any other requirement for a computing system, and then verify and validate the implementation of those safety requirements. One point of specificity in this regulation is that for each computing system safety item that is safety critical by the definition of 401.7, verification and validation must include a testing by a test team independent of the development division or organization. And that level of independence is further defined in the AC. Next slide. So 141B requires that the safety requirements be identified for each computing system safety item, then that those safety requirements be verified, complete, and correct. And that means check that the safety requirements are consistent with the system's safety requirements. That's the overall system's safety requirements. And check that those safety requirements fully specify all needed safety functionality. And last, verify and validate implementation of the safety requirements at the level proportional to their criticality. Next slide. Next are the process requirements of 141C. These are laid out as a process requirement rather than a requirement for a development plan, because the process is necessarily bigger than the plan. This can be in one document, many documents, however the applicant wishes to structure it. But the key element here is that the development process used for each computing system safety item has to meet each of these components at a level that is commensurate with its level of criticality in the system. Next slide, we'll discuss a little bit more about each of these 8 parts. First, A requires assignments of responsibility for development tasks. This is usually by position or title. We're looking for individual resumes, but rather which position or personnel is assigned to each key development task. Second, under B, we require the review processes for requirements or for vetting, implementation, and testing of system requirements. Under C, it requires training and qualification processes for personnel and safety development roles. The expectation here is that the development process should have some specification for who's carrying it out and thereby establish that they're capable of performing their role. The Part 4 requires a process for tracing requirements to verification and validation evidence. This is what enables FAA and the applicant to know that the eventual verification and validation set is complete. Part E requires configuration management, at least to the level that specifies the content of each released version of a computing system safety item. This is related, of course, to 45103C in the broader configuration management requirement. Part F requires a testing process with rigor proportional to the level of criticality of the software of the computing system safety item, with independent verification validation for safety critical computing system safety items. And that independence is at the level of a development division or from the development organization, whether by an independent contractor or an independently operating test group within the overall corporation. The reuse policy needs to define evaluation and testing processes for computing system safety items that are being reused. And then the third-party policy needs to define acceptance or criteria for acceptance, evaluation, and testing of third-party computing system safety items. Next slide. And then the license application requirements in Part D specify what needs to be documented in the application. That is, identify and describe all of the computing system safety items, provide the safety requirements for each computing system safety item. That can be part of the description in number 1. Provide documentation of the development processes that meet 141C. Provide evidence of the execution of the appropriate development process for each computing system safety item. That is, what development process was used to develop the safety item. And then provide evidence of the implementation of each safety requirement. This is the verification and validation evidence. Next slide. In practice, 141D requires exactly that. The identify computing system safety items and describe them along with their criticality in the operation. Provide the safety requirements for each of those safety items, what they do for safety. Provide the development process that makes sure that they are capable of doing their safety tasks. Provide evidence of the execution of the development process. And along with that, to note which development process applied to each computing system safety item and which process path options. Or a development process often has many paths that an individual item can trace through it. And if there are different options that a safety item could follow through a development process, which of those path options have been executed? Then provide the artifacts of the development process that verify that the computing system safety item followed the process. This is typically either test reports, sign-offs at different milestones, there are a number of ways to demonstrate that, and a computing development process produces evidence of its execution along the way. And lastly, to provide the test records, analyses, or other verification evidence as specified by the process for each of the safety requirements. And that is the last of my slides.
Okay. Thank you, Jay. And Cameron, if you want to turn your camera on as well, we can get into some of the questions we received. Just wanted to quickly start the session that I thought might be helpful for some folks. Jay, can you talk about why the name of the section changed from just computing systems and software to just computing systems?
Yes, broadly speaking, there are a number of categories of things that are very close to software, firmware, for example. We wanted to keep this section as general as we could so that we don't need to bother distinguishing between what's software, what's firmware, what's in different categories. The key delineator is the complexity involved in a computation system.
All right. I just thought that might be on some people's minds.
Yeah.
So let's go into the questions, and I urge you guys to go ahead and put your questions in so they can get into the queue. I think we have a couple that have been emailed before the workshop that we'll go over right now. If an applicant is using government furnished software, or GOTS, or COTS software firmware that has undergone formal government IV&V, will the applicant have to verify and validate the safety requirements of third-party products as stated in 450-141C7, or is this requirement only applicable to software not undergone IV&V?
So how that ends up working is that the software developed by other organizations, whether COTS or GOTS, would end up falling under the third-party software use plan required by C8 of Part 141. And so it wouldn't necessarily require replication of the verification validation efforts that the third party had undergone, but rather to define the acceptance, evaluation, and verification evidence that the applicant would use for its third-party systems and for use of that third-party system in its system.
Okay. For an operator launching from a federal range, does compliance with range requirements from 91710 or RCC 319 or 314 ensure the equivalent level of safety is demonstrated, resulting in all Part 450 compliance?
Yes, we can lay that out in our AC so that the compliance with the tailored range documents is one method of complying with 141, specifically with RCC 319.
Okay. The requirements of 450-141C, Charlie, appear to be extensive, not just requirements, development, design, test, IV&V, but also identification and qualifications of the design personnel. Is this level of detail new relative to Part 415, 417?
I would say the level of detail is new, but the expectation isn't really changed. We could probably give a fuller answer to that offline, but I would say that the criteria are similar to 415, 417. The level of detail and granularity is a bit new.
Okay. So similar to the last question, can you in general terms describe the key differences in requirements for the computing safety systems that have been instituted in Part 450? Computer safety items, sorry.
Let's see.
Is Cameron able to join us also? I don't see his camera on. Okay. So I think
This-
if you want, we
This one,
can.
I think, would take this would probably be better for a written response where we could go point by point.
Okay, yeah, we can, all these questions, we're going to provide responses in writing and post it to our website. So let's just go to the next question. It appears that 450.141 of the final rule would apply to software firmware that is part of navigation sources, particularly GPS and IMUs, which are often programmed with closed binaries from the manufacturer, and it may be impossible for a launch vehicle developer to comply with 141, which requires V&V of the requirements and code. This would appear to be out of line with the current precedent that has allowed for tracking sensors to be approved based on heritage of widely used production firmware through testing of unit performance and configuration control. Is this intentional?
The real answer is that the navigation sensors and things with closed binaries would fall under the 450.141 C8 path. And the heritage of those sensors would be part of the acceptance criteria that the applicant would define for using those third-party computing system safety items.
Okay. Is there a more specific definition of independent of the development division or organization that's used in 450.141 B4? It would be useful to have an unambiguous definition that would not be influenced by arbitrary corporate structures in different organizations.
Yeah, we expand on that concept, the independence, in both the preamble to the final rule and in the AC. And we do that broadly by saying that the independent verification validation team needs to have a distinct set of incentives and operating parameters that allow it to be functionally independent of the development group.
Okay.
The discussion's probably better read in those two sources.
Okay, well, and we can certainly summarize those and see if there's more we can add to our written response. We have one more question in the queue, so if you have some questions, please type them in. Right now, the last question is 450.141A. Is the term software intended to include complex electronic hardware, such as custom micro-did components, PLDs, ASICs, or FPGAs?
It, broadly speaking, well, not so much the term software is intended to include it, but computing system safety items could include those complex hardware logic devices.
Okay, I think we might have a couple more questions coming in the queue.
I do see one here about independence testing being iterative.
There you go.
And yes, I would say that the expectation is that the IV&V is not or independent testing is not a single event, but rather an ongoing process that ideally gives timely feedback to the development organization such that they can make iterative improvements as they go.
Great. Any other questions coming in? So if we don't have any more questions, we'll give it another minute for folks to give them time to type. But this is our last session of the day. We will be coming back tomorrow at 10 a.m. Eastern. And we'll be continuing down the prescribed hazard controls for safety critical systems with our sections 450, 143, and 145. And just a reminder, if you have any feedback for us, feel free to use the chat, or if you have questions later that you think of, you're welcome to submit those to your licensing point of contact or to myself, or in the chat or the Q&A functions. Otherwise, I don't think we have any more questions coming in today for this session. Thank you very much for your participation, and we will see you all tomorrow at 10 a.m. Eastern. Thanks, everyone.